researchers have been working on biodegradable materials that can break down more easily, reducing their impact on environment. Materials with quantum properties, that is quantum materials, have the potential to revolutionize computing, communications, and other fields. Researchers have been working on ways to better understand and control these properties. These are just few examples of many exciting advancements in material science that have been made in recent years. That is why we have selected the theme of this seminar is recent trends in material science. Overall, material science research is essential for driving innovation, sustainability, and advancements in various industries, as well as addressing global challenges and improving quality of life of people around the world, which is ultimate aim of scientific research. This conference is a remarkable opportunity for us to come together and explore the latest advancements, challenges, and opportunities in the field of material science. Thank you for being part of this conference and wish you all a stimulating and fruitful experience. Once again, I welcome you all from the core of my heart. With this, I take my leave. Jai Hind, Jai Maharashtra. Thank you very much. Over to Dr. Kalam.
Thank you, Dr. K. Shetty, sir. Thank you for your comprehensive remarks and information about the conference and the motive behind organizing this conference. I am sure the participants will definitely learn some new things in the area of material science research. Thank you once again, Dr. K. Shetty. Now, we'll move ahead to the next part. For the welcome address, I request principal of this college, Dr. B.U. Jadhav sir, for his welcome address. Dr. B.U. Jadhav, over to you.
Can you hear me?
Yes, sir. Yes.
A very good afternoon to all of you, ladies and gentlemen. I, Dr. Balasaheb Jadhav, Principal MSP Mandals, Sri Shivaji College, Parbhani, welcome you all for this international conference on recent trends in material science 24, organized by Department of Physics and Electronics of our college in online mode. It gives me immense pleasure, pride and honor to see all online for this conference. Inaugurator of this conference of our college, Mr. Dr. M.K. Patil sir, Dean Science and Technology, Swami Ramanand Tirtha Maharashtra University, and also head, I think, Dean of the University, all the participants, Honorable Hemantrauji Zamkar, faculty members, researchers, students, industrialists, Vice Principal of our college, Dr. Srinivas K. Shetty sir, Dr. Rohidas Nitunde, member of the organizing committee, member of advisory committee, honorable resource persons, welcome to one and all. At the outset, I thank all the participants for their overwhelming response. I feel proud to introduce you to my college. This college, MSP Mandals Sri Shivaji College, is located at Parbhani, which is a district place in the Maharashtra region of Maharashtra state, India. Is said to be a cultural capital of Maharashtra region due to its rich cultural heritage and traditions. There are many places of historical importance in this district, like Charthana, Pathri. Pathri, in Pathri, there is a Sai Baba Center, birthplace of Sai Baba. Mudgleshwar Temple, Mudgal, Pardeshwar Temple in Parbhani, Sri Narsimha Mandir, Ukharni, Hazrat Turab ul Dargah in Parbhani, Sri Neminath Digambar Jain Mandir in Nawagad, Sri Digambar Jain Kendra Jintur, etc. Our college is run by Marashwada Shikshan Prasarak Mandal, the largest educational institute in Marashwada region. Present president of our institute is Honorable Prakash Ji Solanke, MLA, and Secretary Honorable Satish Bhau Chauhan, MLC. Our institute, established in 1959, has the largest network of schools, large number of junior colleges, senior colleges, polytechnic, engineering college, law, B.Ed, then pharmacy college, spread over 6 districts in Marashwada region. Our institute is committed to quality education and excellence. Almost all degree colleges have completed a 4th cycle of NAAC accreditation. Considering the effort taken by our institute in the field of education, Government of Maharashtra has awarded a Best Educational Institute to our Marashwada Shikshan Prasarak Mandal. Our college, Sri Shivaji College Parbhani, was established in 1961. We offer education in arts, commerce, science, and management stream. We run 6 UG courses, 15 PG courses, and more than 10 certificate courses. 4 departments are recognized as a research center, in which our department, physics, then chemistry, botany, and zoology. More than 50 students are pursuing research, leading to PhD degree in these departments. More than 5,000 students are taking education in our college, which is spread over 20 acres located in the heart of city. This college is the first college to be established in Parbhani and Hingoli district. We have well qualified staff, well equipped laboratories, a rich library with more than 1 lakh books, large playground, indoor and outdoor sports facilities, girls and boys hostels, auditoriums, clean and green campus with botanical garden, NCC and NSS support services. The college is confirmed. College is committed for excellence in quality education. This college has completed 4 cycle of NAAC accreditation. In the last 2 cycle, the college is accredited with A+ grade, having highest CGPA among all accredited college in this Swami Raman Tirtha Marashwada University, Nanded. The college is identified as a college with potential for excellence. The college has received grants from UGC under STRIDE, Paramarsh, Unnat Bharat scheme. The college is recently selected as a star college. It is the scheme from DBT. The college has received Best College Award, Best Examination Center Award, Best Principal Award, Best NSS Unit Award by the University, Best NSS Program Officer Award from the state of Maharashtra. The college organized student-centric program and capacity building program for the staff. Today's conference is the part of this. I hope today's conference on recent trends in material science will definitely achieve its objectives and goal and serve the purpose for which it is organized. This conference will have the privilege of listening to insightful presentation, enjoying the thoughtful, provoking discussion, and enhancing ideas that will shape the future of material science from nanomaterial to advanced composition, from renewable energy materials to biomaterials. Our conference will cover a broad spectrum of topics that are crucial for development of new materials and technology. I encourage all of you to actively participate in the session and share your expertise. Let us seize this opportunity to learn from each other with new collaboration and inspire one another to push the boundaries of what is possible in material science. I once again welcome you all and extend my best wishes to the conference. With these few words, I take my leave and give you a best luck to all the participants, the organizer. I also thanks the convener and our Department of Physics, Dr. K. Shetty sir, then from Electronics, Dr. Jingre sir, and their staff. With these few words, I give you the best luck and I leave the meeting. Jai Hind, Jai Maharashtra. Have a nice time to you. Thank you. Thank you very much.
Thank you, Dr. B.U. Jadhav sir, for your welcome address. You always lead from front and motivate us to organize such type of events in college on regular basis. I'm also thankful to you for briefly informing about the institute to the fellow participants. Now we move ahead for the formal inaugural of this e-conference. I request the chief guest of this e-conference and inaugurator, Dr. M.K. Patil sir, to formally inaugurate this e-conference and deliver his chief guest address. Over to you, Dr. M.K. Patil sir.
Yeah, thank you very much, Dr. Vijay Kalamse. Am I audible?
Yes, sir.
Good afternoon to you all. Hello, am I audible?
Yes, sir.
Okay. Good afternoon to you all. Chair of this today's international e-conference, though it is organized in virtual mode, we have Dr. B.U. Jadhav, principal of this Shivaji Mahavidyalaya, Parbhani, Honorable Dr. Hemantrao Jamkar, who is a driving force for the various kind of activities that are being planned by the Shivaji Education Society, MSP Mandala and Shivaji College. Co-convener of this today's conference and my friend, Dr. S.N. K. Shetty. Dr. Jingre, who has beautifully written one of the best song for the college, which is called as the Manus Ghadto Yete. I was really inspired by watching that song when it was played on the screen. Other colleagues from the Physics and Electronics Department, Dr. Yanurkar, Dr. Vijay Kalamse, IPSC coordinator, and my friend, Dr. Nitonde, all the distinguished guests, speakers, Dr. Pasha Sayyed, to whom I can see on the screen over here, esteemed scientists, young researchers, and my colleagues. I am extremely honored to address you on this momentous occasion of International Conference on Recent Trends in Material Science, ICR TMS 2024. Indeed, it's a great pleasure for me to interact with you all, though it is a virtual one. Friends, I was told that this conference on recent trends in material science is being organized by Shivaji College, Parbhani, as a part of celebration of the National Science Day. We know The National Science Day, which is every year celebrated across the country on 28th of February. This is one of the very important occasion wherein we encourage all the young brains, young minds to make their career in the fields of science and technology. First of all, before actually starting with my inaugural address, let me declare that I hereby declare that the International Conference on Recent Trends in Material Science is formally inaugurated. Thank you very much. As per the Louis Pasteur, we know he is one of the pioneering researchers who has given us a very beautiful vaccine and has helped the humankind not only in his own country but across the globe. So as per his vision, he states that science knows no country because knowledge belongs to humanity and is the torch which illuminates the world, which are a perfect depiction of the solidarity that binds all the nations together. Friends, in the same vein, let me mention over here that the Sir C.V. Raman, contributions made by Sir C.V. Raman, which are commonly known as Raman effect, are significantly important. On the National Day, we celebrate his work and across the country, which has inspired generations of scientists in our country and beyond. The Raman effect was a groundbreaking discovery that paved the way for the development of the modern physics and changed the course of scientific research. The discovery not only enabled Sir C.V. Raman to earn the Nobel Prize in Physics, but also put India on the global scientific map. So to commemorate his work, contribution, we normally celebrate 28th February as the National Science Day, and it came from the mind of the then Prime Minister, late Rajiv Gandhi ji, who in 1987 thought that it is a requirement across the country to inspire the young brains to make their career in the exciting field of science and technology. And since then, 28th February is being celebrated as the National Science Day. It also highlights the importance of the scientific research in driving progress and innovation in various fields. We know the Raman's work, Raman's contribution is very significant, and particularly in material science, it has been in use in a variety of ways. Electromagnetic radiations, whenever it passes through that of some material, it interacts with it and gives some beautiful results in the form of what are called as the Stokes and anti-Stokes line. These two additional frequencies, which were observed by Sir C.V. Raman through his very simple experiment called as a Raman effect, making use of a small spectrometer, a source of electromagnetic radiation like a light source, and some organic material. He realized that the radiation that is emerging out of that organic solvent, it not only carries the original frequency, but in addition to it, there are two more additional frequencies, one which is slightly lower than it and another slightly higher, which he called them as the Stokes and anti-Stokes line. Though it was a very simple experiment, but has given us a very beautiful result, and that has been in use in variety of fields, including the medicinal sciences, advanced researches in material science, and even in other cases also. So to commemorate this beautiful discovery, we are celebrating National Science Day. And on this occasion, Shivaji College Parbhani is organizing International Youth Conference on Recent Trends in Material Science. I think it is one of the best opportunity to celebrate this discovery of Raman effect. And therefore, I congratulate all the members who are contributing significantly in organizing this international e-conference. Particularly Principal Dr. B.U. Jadhav, Vice Principal and my friend Dr. Srinivas K. Shetty, all the organizing members, IQAC coordinator, and even the speakers who have taken a lot of efforts in making this conference successful. We know this in the present era, 4 technologies are playing significant role. One is biotechnology, another is energy technology, third is the space technology, and over and above all these 3 technologies, the advanced technology, which is called as nanotechnology, is encompassing all such recent advancements. And that is the reason why the research in material science, particularly in the present era, is very important. This Raman effect, as I mentioned, is playing a very important role in making newer advancements in the studies, in particularly in material science, in other branches like that of the medicinal sciences, and so on. In the vast landscape of scientific inquiry, the realm of material science stands as a dynamic crucible with wide range of innovations and discovery. As we embark on this journey through the progress of recent trends in material science, we find ourselves at the crossroads of tradition and cutting-edge exploration. This international conference, serves as a golden opportunity for the researchers to traverse the ever-evolving terrain of material research, a discipline that has ceaselessly pushed the boundaries of human understanding. As we delve into the recent developments in the field, you will witness the seamless interplay between the theory and experimentation, where scientists unravel the secrets held within the molecular complexes of material. From the inception of innovative synthesis techniques to the applications of advanced characterization methods, innovations in material science has witnessed remarkable advancements in recent years that has not only revolutionized industries in general, but has also opened new possibilities for the startups across the India. And in the coming time, you will see that because of the more and more advancements in the material science research, we will see that India by 2047 will emerge as the developed country. So the material science is not only limited to the research in the complexes of molecules and so on, but it has several other wide range applications. As was mentioned by Dr. K. Shetty in his opening remarks, in aerospace and aviation technology also, industry also, this is being widely used. The aerospace and aviation industry has benefited from lightweight materials that enhance fuel efficiency and performance. The high performance materials which are being used widely for the design and making of the spacecraft have made it possible for the space exploration with a great safety. You may recall the sad demise of one of the lead lady researcher, Kalpana Chawla, who was of Indian origin. On the space voyage, when she was returning back to motherland, she met an accident, and it was because of a great friction between the atmosphere and the aircraft. Had it been possible for us to use such type of lightweight and very strong materials, which now we have with us through the recent developments in material science, probably we could have saved her life and therefore could have reached even more heights in the domain of space explorations. So such type of high temperature sensitive or resistant materials, which are nowadays are being used for the spacecraft design, which in the form of advanced coatings and surface treatments are certainly improving the durability and protection of such aircrafts. In the domain of energy and environment sector, energy generation and storage have gained prominence. From solar cells to batteries and environmental remediations, material science is contributing significantly. Electronics and optoelectronics is another domain where the recent advances, researches in material science have seen the breakthroughs in semiconductor materials. Friend, recall the time of a couple of decades back when the first computer was prepared. You might be knowing that it was made by making use of thousands of vacuum tubes, and a wire of about several thousand kilometers. It required several megawatt power for its operation. And now we have very soft, very fast and very advanced computers which are operated at a very low voltage. The smartphones, what we have today with us, they are much faster and bigger computers compared to that of the first machine which was designed. So all it has become possible because of the advancements in the semiconductor technology, and its credit goes to the material scientists. So the flexible and variable electronics offers new avenues in the coming time. The photonic materials, which are again some of the most advanced materials that are being used in telecommunication and sensing technology, that are also proving their capabilities in various ways. It is not the only case that we are using such a recent research trends in designing of materials and other things, but in the domain of healthcare and biotechnology, material science has played a significant role and have transformed biocompatible. They have designed biocompatible materials which are widely used. I'm sorry, which are widely used for the implanting purposes, for the drug delivery purposes, for the tissue engineering. So these materials are enhancing the patient outcomes and promoting regenerative medicines. Future knee implant will be personalized to meet the exact needs of each body, both in terms of structure and composition. And I suppose it has become possible only because of the advancements, because of the research in material science. With the help of artificial intelligence and quantum computing over the next decade, you will see that the discovery of new materials will accelerate exponentially. Transportation and automotive industries are also getting benefited from the design and uses of lightweight and high strength materials, which is not only key role playing in reducing the fuel consumption and emission, but is also enhancing the life of such type of vehicles. The 3D printing, which is being widely used in majority of the domains, that will also play certainly a very significant role in the recent advancements or future developments in the material science. So the future prospects and emerging trends in material science not only include the design and preparing of newer materials, but with the help of the computing, 2D materials, bio-inspired materials, additive manufacturing, and machine learning for the material discovery, these advancements hold promises for revolutionizing computational speeds as well as electronics and sustainable technologies. Continued research in collaboration with that of the lead researchers across the globe, their ethical considerations will shape the future of material science, further driving technological advancements for the future society. The landscape of material science is not merely confined to the laboratories and academic institutions, but it is extended to the tundles into industries and everyday applications. Thus, the discoveries made in the recent past bear the potential to revolutionize fields of diverse as electronics, healthcare, energy, and beyond it. As we stand on the principle of new breakthroughs, the collective pursuit of knowledge is paramount. May this conference on recent trends in material science that is being organized by Shivaji College, Parbhani, serve as both a testament to the achievements of the past and compass guiding us towards the uncharted territories of tomorrow. Once again, I take this opportunity to welcome you all on this for this e-conference on recent trends in material science, and thank the organizers for giving me this opportunity to interact with you all, though it is a virtual mode, and giving me this opportunity to inaugurate this program. So thank you very much.
Thank you, Dr. M.K. Patil, sir, for your address. You have very nicely emphasized the importance of material science research and their applications in various domains of science and technology, such as space technology, energy technology, nanotechnology, biotechnology, and many more sectors. Thank you for accepting our invitation for this event. And once again, I thank you on behalf of the organizing committee and Sri Shivaji College, Barbani. Thank you, sir. Now I request Dr. Surendra Yenorkar, sir, for the vote of thanks for this inaugural session. Over to you, Yenorkar, sir.
Thank you, Dr. Karan sir. All participants, esteemed guests and dignitaries, a very good afternoon to you all. It is with great pleasure and gratitude that I extend my heartfelt thanks to each and every one of you for gracing the inaugural ceremony of our international online conference on recent trends in material science. I extend my sense of gratitude towards Honorable Mr. Hemantrao Jamkar, Sir, CDC Head, Sri Shivaji College, Parabani, for his gracious presence in this inaugural function. First and foremost, I extend our deepest appreciation to our inaugurator, Professor Dr. M.K. Patil, Sir, Dean Faculty of Science and Technology, SRTMU, Nanded, among us today for gracious this occasion. With his esteemed presence and inaugurating this conference. Your inspiring words have set the tone for what promises to be stimulating and enriching event. I would like to express our sincere gratitude to Principal of our college, Dr. B.U. Jadhav, sir, whose continuous support and guidance have been helpful in bringing this conference to realization. Your leadership has been a model for inspiration for all of us. A special word of thanks to our convener and vice principal and head, Professor Dr. S.N. Keshetty, sir, co-convener R.P. Jingre, sir, for their meticulous planning and tireless efforts in coordinating every aspect of this conference. Your dedication and attention to detail have ensured the smooth execution of this event. We are also grateful to our Vice Principal, Professor Dr. R.S. Nitonde, sir, and IQAC Coordinator, Dr. U.B. Kittekar, sir, for his continuous support and encouragement throughout the planning process. Your presence here today underscores the importance of this conference for our institution. Last but certainly not least, I extend my gratitude to all the participants who have joined us from different parts of the country and abroad. Your presence here today signifies your commitment to advancing knowledge and fostering collaboration, and we are honored to have you with us. I would like to express our heartfelt gratitude to all HODs and all the staff members of our college for their persistent support and guidance. Once again, thank you to our inaugurator, distinguished guests, and all the participants for making this inaugural ceremony a memorable and inspiring occasion. Thank you, one and all.
Thank you, Dr. Yenorkar, sir, for proposing vote of thanks. Now, we are moving towards the technical session, but prior to that, with the permission of the chief guest and the president, I declare here that the inaugural session is over. Dr. Pasha, sir, are you ready?
Yes, sir.
Syed, sir.
Yes.
Okay. So, sir, are you able to share your screen?
Yeah. I have just shared now. Can you please tell me, is it visible?
Yes.
Okay, sure. Thank you.
Yes, sir. 1 minute, then we can start.
Yeah, sure. Please let me know. I will start then.
So now in the technical session, we have 3 invited talks of 1 hour each. So the first talk will be delivered by Dr. Pasha Sayed sir, who is postdoctoral research fellow, Department of Electrical Engineering, American University of Sharjah, United Arab Emirates. He will talk on the topic, the functional nanomaterials for advanced sensing and device applications. So, before his talk, I'd like to request Dr. G.B. Gundewar sir to introduce our first guest.
Thank you, Galamse sir. Good afternoon to all. It's my pleasure and honor to introduce our distinguished speaker for this session, Dr. Pasha Sayed sir from Department of Electrical Engineering, American University of Sharjah, United Arab Emirates. He is presently working as postdoctoral fellow in the Department of Electrical Engineering at the American University of Sharjah, United Arab Emirates. He was a postdoctoral fellow at the Department of Electronics, Materials Engineering, Wangun University, Seoul, South Korea, during 2023 to January 2024. He also had a teaching experience of 2 years at graduate and postgraduate level. Dr. Pasha Sayed completed his PhD in 2021 under the valuable guidance of Professor Mahendra D. Shirsat at the Rusa Center for Advanced Sensor Technology, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, India. Currently, he is working on a neural engineering research project, and his field of expertise include developing 1D and 2D nanomaterials with organic conducting polymers and their applications in heavy metal ions and gas sensors. With this brief introduction, I request Dr. Pasha Sayed sir to deliver his talk on functional nanomaterials for advanced sensing device applications. Over to Dr. Kalamse sir.
Dr. Pasha sir, you can proceed with your talk now.
Okay, sure. So I hope or I consider that my voice is audible to everyone, and I will proceed.
Yes, your voice is audible and your screen is also appearing.
Okay, sure. Thank you so much. So first of all, I would like to thank you, Chief Patrons and the organizers of the conference for giving me the opportunity to deliver my talk or inviting me to deliver a talk. So in today's conference, recent trends in material science, I am going to discuss about the functional nanomaterials and advanced sensing devices, like the kind of how these advanced sensing devices can be manufactured, that micron scale devices can be manufactured for the sensing application. So to begin with, these are the outlines of my presentation. So in which I am going to discuss about the introduction, the types of sensor, then why and what is the significance of nanomaterial and why it is particularly suited for sensing application. Then I will discuss about the FET sensing device fabrication process and its application for heavy metal ion sensing. And then there is some alternative manufacturing process, sensing manufacturing process for gas sensor application. And then I will conclude my talk. So sensor is broadly categorized into two parts. The first is physical and the second is chemical sensors. So mainly I am working in chemical sensors, that is heavy metal ion sensors and gas sensors. So I am not interested in physical sensors like motion, density, temperature, pressure, etc. So I am working in chemical field effect transistor sensors and gas sensors. So the question is like why the biosensors and gas sensors are continuously growing in the market. Because as we can see here, the figure in the left hand side. So biosensor is having huge application in water monitoring, drug delivery, pathogen, soil monitoring, etc. And we can see here the sensor market is continuously growing. We can see in 2022 the biosensor market was around 27 million, and it is expected to grow 63 million in US dollar in about 2032. So therefore, this field is continuously growing as we consider about the same for gas sensor and biosensor. So that is why I am very much interested in pursuing my research in gas sensor and biosensor technology. So now the functional nanomaterials. So if we have to detect any analyte or gases, so first question is to like what kind of material we should select for the sensing application. So in my field of expertise, I am working on the organic conducting polymers, graphene, and some peptide modification. To begin with, we can start the organic conducting polymer. So this organic conducting polymer is having excellent properties like lightweight, it is flexible, electrically conductive, and portable. So since my research area includes the heavy metal sensor, like the kind of water sensor, so the material that I'm going to explore for the sensing, that should be that should have water stability, so that the sensing performance can be improved. So I have selected this organic conducting polymer, and among this I'm working on the P.PSS conducting polymer. But the problem of this organic conducting polymer, it has low conductivity and low mobility. So in order to improve the mobility and the sensitivity, I have like in my research area, I have chosen the graphene oxide, reduced graphene oxide, and carbon nanotubes. Because the graphene, let us discuss the graphene. So graphene is two-dimensional material with excellent properties such as it has high surface area around 400 to 1000 meters square per gram, high mobility, good mechanical strength, and high sensitivity. And the third one is like carbon nanotubes. So this is one-dimensional material. It also has the similar properties as graphene. It has high surface area, mobility, good mechanical strength, and high sensitivity. So once I will add this nanomaterials, two-dimensional nanomaterials in conducting polymer. So I was expecting to increase the electrical conductivity, and so because in sensor I am particularly focusing on the selectivity and sensitivity. So this fourth material, that is peptide, this is kind of a molecular linker. So this peptide I have modified to the P.PSS and like graphene composite to inculcate the selectivity. Now let us see some fundamental of the graphene, what is graphene, and like how the from graphene sheet it becomes the single wall carbon nanotubes and multi-wall carbon nanotubes. So this figure A is graphene layer, the single layer graphene layer. If you roll this single layer graphene, it becomes single wall carbon nanotubes. And if we have multi-layer graphene, and if we roll it, then it will become like multi-wall carbon nanotubes. So this way, this single layer and multi-layer graphene and CNTs can be synthesized with different technique like CVD, chemical vapor deposition, PVD, physical vapor deposition, MOCVD. There are many techniques which we can grow these nanomaterials. So initially we will discuss about the how sensor work, like how the typical sensor will work. So here there are two kinds of input, like physical and chemical sense. So in my case, I am working in chemical sensors. So this this target analyte interact with the sensor and send the signal to the signal conditioning element. And this signal conditioning element process the information and gives us the data in the form of electrical signal. So this is overall working of the sensor. Now, as the first step in order to fabricate micron scale devices for sensing application, the first step is to design the photomask. So designing a photomask is the first step in the fabrication process. So I have chosen in my doctoral study the interdigital electrode. So the figure A, we can see the interdigital electrode design, which is having 10 mm in length and 5.6 mm in width. So this interdigital electrode is having total 6 fingers, and each finger is having 0.1 mm size, and the distance between these two finger is 0.003 mm, like a kind of 3 micron, and the actual image is shown in the figure B. So this is the photo mask just for the sensing device fabrication, and we fabricated this photo mask from Seri, Rajasthan. This photo mask can be fabricated using electron beam lithography. So, and the design can be like this design can be made in AutoCAD, and then you can prepare the different kind of designs. So in photo mask also there are two types of photo mask. It depends on the kind of application you are using, because the sensor technology, as we have seen in the introduction section, it is continuously growing. So depending on the application, like you are using for what kind of person, for implantation, or for some biomedical field, or some biosensor application. So it depends. So the figure on left hand side, it just shows the two types of photo mask. The left side, the first indicates the bright field photo mask, and the right is dark field photo mask. And in both of these application, here the positive photoresist is used. So we can see here. So if we have positive photoresist, because selection of photo mask is very important, like because we need to know what kind of design we want. Here we can see, if we want the island type design, then we can use the bright field photo mask. Then we can decide, okay, the bright field photo mask will be suitable for our application. And if it is like we want to create the window, we can use the dark field photo mask. So these are the example, the actual photo mask that we have with in our laboratory in Rusa Center for Advanced Sensor Technology, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. So we have both masks, bright field photo mask and dark field photo mask. With the help of this, we can fabricate the sensing devices. So this is just for the idea, like I have discussed about the different design can be, the designs can be like formulated. So these are the different designs. So figure in the left side, these designs are for micro heater. Like for example, if someone is working on gas sensor and particularly on metal oxides, so everyone knows that the metal oxide based gas sensor operate at very high temperature. So the researchers, what they are doing, they are just fabricating this micro heater at the backside of the device, and so that the external temperature can be applied, and how they can reduce the operating temperature. So these are different types of designs on the left side, and the right side. This figure is like the kind of, for example, if I want to fabricate the microsensor array, so the kind of array we can design the sensor array also for the different types of sensing application. Now the second step is this whole process is called photolithography process for FAT device fabrication. So during this process, so once we finalize the photo mask, then we have to decide the photoresist. There are two types of photoresist. One is positive photoresist and second is negative photoresist. So the positive photoresist, like we can see, when the light is exposed to the positive photoresist, the exposed area will be removed, and unexposed area will remain on the substrate. So this way the positive photoresist will work. Whereas in the negative photoresist, the unexposed area will be removed and the exposed area will remain on the substrate. So the selection of photoresist is also important while fabricating the devices. So this is overall process flow, like how the sensing devices can be fabricated. So initially we have taken the 4-inch silicon dioxide wafer that can be seen in figure A. So this is 4-inch silicon dioxide wafer with p-type boron dope p-type, and its orientation is 110. So once this wafer is cleaned, so this all process, in order to fabricate micron scale devices, we need a clean room that should have very less amount of dust particles, which is having the size of 50 less than 50 micron. So this initially the silicon dioxide wafer is cleaned with acetone and isopropanol, and then the photoresist is spin coated on the substrate. So before spin coating the photoresist on the substrate, after cleaning, this wafer is exposed to the dehydration bake to remove the organic residues and some water molecules, and then the AZ5214E photoresist. So this is image reversal photoresist. I can use this photoresist for both positive and negative. So once the dehydration is done, then the photoresist is spin coated onto the substrate, and after spin coating of photoresist, there is a step we call pre-bake. So we have to pre-bake this photoresist at 100 degrees Celsius for 50 seconds, so that we can proceed this steps to the next step. So once the pre-bake step is done, then UV light is exposed through the mask. So this, when we expose through the mask, then we can see the exposed area. Now this photoresist is working as a positive photoresist, so that negative photoresist, so that unexposed area is like it is still there, unexposed area is removed, and then once the coating is done, then this solution is deep into the developer. This whole wafer, the wafer containing like our silicon dioxide and then photoresist. After this, we have to spin coat. We have to deposit the chrome and gold for the electrical contacts. So for the electrical contacts, like the chromium here, we cannot directly deposit the gold metal because gold is having poor adhesivity. So the chromium need to be deposited before depositing the gold metal. So once the gold metal, the chromium is deposited by E-beam evaporation, and the gold is deposited by the thermal evaporation. So once the chrome gold is deposited, then the final process is lift up process, that is removal. So this whole wafer is deep into the removal solution by preparing the solution 1:1 mixture with water, and after a few minutes we can remove this, and so that we will get the this type of devices. So here we can see the overall process, overall sensing device fabrication process, in which I explained in the previous slide. The first is cleaning, the second is like pre-bake, and then third is spin coating of photoresist, then post-bake. Then in figure E, we can see the UV light exposure through the mask, and after exposing the mask, the exposed area is removed, and we got the window type structure. So using box like 20 nanometer of chromium and 180 nanometer of metal beam is deposited, and the figure H shows the final 4-inch device which has many devices. So these are the some optical images. So we can see here the top right side, the silicon dioxide wafer with our sensing interdigital electrode design pattern on the substrate, and the distance between these two fingers is 3 micrometer, and the chrome gold deposited substrate. Now, once the device fabrication is done, now the next step is synthesis of material, because mainly my research areas include the fabrication of sensing devices, synthesis of material, characterization, and its application for sensing application. So here in this paper, I have synthesized P.PSS, RGO, and L16 nanocomposite. So initially, I synthesized graphene oxide, in which the separate two solution A and B is prepared. So first solution is graphitic powder and second is KMnO4. They are well mixed together. And second solution, that is B, acidic solution, that is phosphoric acid and sulfuric acid. So slowly, if we add the above solution A, the solution B, then the graphene oxide can be synthesized. So this whole process of graphene oxide synthesis can be done by using improved Hermann's method. So once the graphene oxide is synthesized, then using chemical method like kind of hydrogen hydrate, I have reduced this graphene oxide to the reduced graphene oxide, and then using simple solution processing method, the composite of P.PSS, RGO, and L16 is prepared. So once the composite is prepared, then we need to characterize our material, whether it is properly synthesized or not, the well suitable characteristics that for sensing application. So here in figure A, B, C, and D, it shows the SEM and EDS analysis of the material. So figure A is related to P.PSS, B is related to RGO, figure C is related to P.PSS, RGO, and figure D is P.PSS, RGO, L16. So figure B, here we can see the graphene sheet, and in figure D, figure C we can see that is P.PSS, RGO. So in EDS spectra, we can see the presence of this sulfur atom, which confirms that the presence of this in figure C, we can see the atomic ratio of carbon is increased, and this graphene sheet looks like slightly wrinkled and crumpled type. So that is due to the formation of pi-pi stacking between the P.PSS and RGO. And once the P.PSS RGO is synthesized, the next step is to modify this P.PSS RGO with L16. So the modification can also be confirmed by the EDS and SEM also. So EDS spectra like L16 contains nitrogen group, NH2 group. So the presence of this nitrogen indicates that the L16 has been successfully modified over the surface of P.PSS RGO composite. Now this figure C, this is like the morphology, the structural characterization of all this material, P.PSS RGO, and L16 modified P.PSS RGO. Here in the XRD spectra of P.PSS, no peak was observed. That is because the P.PSS is amorphous in nature. So that is why there is no peak in the P.PSS. The second is reduced graphene oxide. Here we can see there is broad peak between 25 to 30. So this broad peak in reduced graphene oxide is attributed to the sp2 hybridized carbon atom in the graphene lattice. And when this RGO is added to the P.dot PSS, the interlayer spacing is increased, which confirms that the RGO is successfully added to the P.dot PSS. And in the final composite, the P.dot PSS RGO L16, the XRD very highly crystalline peak is observed, which indicates that this highly crystalline peak is related to the sulfur SH atom in the L16 also, because L16 contained three main functional group: thiol, that is SH, carboxyl, COH, and third one is NH. So this peak is due to the sulfur containing L16. Now the next is electrical characterization. So far we have seen I have synthesized, I have fabricated the device. Then the next I have synthesized the material, and the third process is like the confirmation whether the proper characteristics of the material is synthesized or not. Now the next step is the electrical characterization. So this figure A shows the schematic of the FET sensing device. Figure B is IV characteristics, in which we can see the current level in the P.dot PSS RGO and P.dot PSS RGO L16 is substantially increased. So that is significant, and that is the goal of my research, to increase the conductivity, like mobility, so that the sensitivity can be achieved. Figure C and D is the output and transfer characteristics of the P.dot PSS, and E and F is the P.dot PSS RGO output and transfer characteristics. So as compared to the P.dot PSS, the current level in the P.dot PSS RGO is increased. So that is due to the addition of highly conducting reduced graphene oxide and due to the sp2 hybridized carbon atom. So that sp2 hybridized lattice structure provides pathway for the charge transfer. So that is why the increase in current is observed in the P.dot PSS RGO composite. And the final, after modification, the final composite is exhibiting the p-type behavior with excellent output and transfer characteristics. Now, once this is confirmed, the next step is to sense the heavy metal. So this table indicates that from the transfer characteristics curve and using the drain current equation, the mobility and on-off ratio is determined. So as here we can see the mobility of the composite, the P.dot PSS increased. The earlier the P.dot PSS is having mobility 0.00549 centimeters square per hole per second. And after adding RGO, the mobility and on-off ratio, both values are increased. So using this drain current formula, the mobility and on-off ratio is determined. The next step is detection of heavy metals. So figure A shows the real-time response of copper and lead ions. So this copper and lead ions, before going to sensing, first of all, like this copper and lead ions containing DI water. So first of all, we have to measure the baseline. We have to see what is the effect of only the solvent, like the DI water. So I have recorded this drain current response first with DI water, then copper and lead, and found that the copper is having higher drain current change in the sensing application. Then the sensing is done in two modality, the transfer characteristics as shown in figure B, and figure C is related to output characteristics. So the same way, the figure D and E is for lead ions, figure B and C just the for copper ion sensing in both modality, transfer and output characteristics, and figure D and E is transfer and output characteristics for the detection of lead ions in the transfer and output characteristics. So the different types of heavy metal concentration is prepared using the dilution formula and drop cast it on the channel material. And as the concentration of heavy metals increases, the drain current is decreased. So this sensing mechanism is like the kind of gating effect. Now let us see the sensing mechanism, like how this P.PSS RGO L16 is selectively detecting copper and lead ions. So here we can see the L16. So this L16 consists of 3 groups: carboxyl, COH, thiol, that is SH, and NH2. So this L16 is binding to the P.PSS RGO through the carboxyl group, the hydrogen bonding, and there are many active sites to capture the heavy metals through the thiol and amide NH2 group. So this functional group capture to the heavy metals like kind of copper and lead ions, and this way the sensing of heavy metals has been done. So once the sensing is done, then these are the 2 calibration plots for copper ions and lead ions, and we achieved the low detection limit for copper ion 0.33 microgram per liter, and for lead ions 2.36 microgram per liter, which is well below the WHO threshold, World Health Organization. Because the World Health Organization, this decide the what should be the contamination level in the drinking water of these heavy metals, and we achieved less than that value. So now the second, so now this is the end of one process, like the fabrication of sensing devices using photolithography process. The second is the synthesis of characterization and synthesis, and the second is characterization to confirm whether the material is properly synthesized or not. And once it is confirmed, then the electrical properties and the detection of heavy metals. Now the next my next area of research is gas sensors. As we have seen in introduction section, the gas sensor is also having huge application, and recently many researchers, they are exploring gas sensing for breath analysis, because this is kind of non-invasive technique. Because the invasive, like kind of, for example, if you take the example of diabetes, there are conventional ways in which if someone goes to hospital, they will go to the doctor, so they will pinch their they will just puncture their body, take out the blood, and they do some laboratory test. So based on that test, they will come to know that your diabetes level. But now there is huge research is coming in the way, like this diabetes can be detected by the breath analysis. So when we breathe, like there are many VOCs and gases are present. So by discriminating that particular gas, for example, if the person is having diabetes, so he will exhale more amount of acetone. So if we could detect this acetone from the exhale breath, so that we can determine whether the patient is having diabetes or not. So that is why this gas sensing research field is highly emerging. So to begin with, for gas sensing application, I have synthesized the same graphene oxide with the improved Hammers method, then make the composite of P.PSS RGO, and then its structural characterization. So here we can see in XRD spectra, that is figure A, the graphene oxide is having sharp peak. So the sharp peak is associated with the oxygen containing functional group, and this peak indicates the well-defined stacking of graphene layers and the interlayer spacing, so which indicates that the graphene oxide is successfully synthesized. So that is the main characteristics peak in the graphene oxide. And in the P.PSS and graphene oxide composite, the reduction in this peak indicates that the graphene oxide is incorporated between the layers, and that is why the intensity in the oxide is reduced. The next confirmation is Raman spectroscopy, that is spectroscopic characterization. So the graphene oxide is having both peak, D band and G band, and in P.PSS there are particular peaks for P dot and particular peaks for PSS. So the presence of this P dot peak in the P.PSS graphene oxide composite confirms that the graphene oxide is successfully incorporated into the P.PSS and composite is successfully synthesized. Next, we studied the morphological characterization, so that we can determine the surface area and average surface roughness. This is particularly very important in gas sensing application, because higher the surface area, there is higher higher the chances to interact the target gas with the material. So we can see here the surface area of graphene oxide. So this figure C, D and E is 3D AFM images of graphene oxide P.PSS and graphene oxide P.PSS composite. So the graphene oxide is having surface area 9.6 micrometer square, and P.PSS is having surface area 9, and surface roughness, average surface roughness, we can see the P.PSS is very smooth, so it is having the surface roughness of only 2.8 nanometer. Sorry. So once we add this graphene oxide to the P.PSS, the surface area is average surface roughness is doubled, and that is useful for the gas sensing application. Now this is the experimental setup. We can see the figure on the left hand side, that is A. So as I discussed in my previous slides, so the sensor devices can be fabricated with highly sophisticated clean room facility. You require lots of high-tech equipment. So for every research center, it is not possible to get that kind of facility. So I'm just showing this paper to just for the like the alternative way. So we can use the copper clad, and we can fabricate different kinds of printed circuit boards that can be utilized as a gas sensor application. So I have synthesized the same kind of interdigital electrode, but with higher dimensions. So there the dimensions was the channel length was like 3 micrometer, but here it is almost 1 mm. So if you do not have the facility like clean room facility or high-tech equipments, so you can simply use the copper clad and using iron etching. So you can fabricate different kinds of sensing devices, and you can also do the sensing. So this is experimental setup. Then the figure B is experimental setup, on which we can see the two gases, then the two MFCs, and this is the gas sensing is done by using K32400. So this is actual performance of the gas sensor. So here we can see the P.PSS and P.PSS GO IV characteristics. So after adding graphene oxide to the P.PSS, the increase in current was observed. That I already discussed with you. That is due to the presence of sp2 hybridized carbon atom that provides pathway for the charge transfer for the charge carrier. Then next, I use this P.PSS GO composite for SO2 sensing. in the range of 0.5 ppm to 40 ppm, and as the concentration is increases, the change in resistance was observed. So this is kind of chemiresistive. Chemiresistive means the change of resistance, and from this the response time and recovery time, these two, whenever we are working on the gas sensor, there are 3-4 parameters which is very important to be improved. First is like the response time, the second is recovery time, and the selectivity and the sensitivity. So the response time of this fabricated gas sensor was 81 seconds and the recovery time was 92 seconds, which is enough for the real-time application. Then once the dynamic gas sensing is done, then we have tested this SO2 gas sensor for selectivity test, and among these 5 gases, the PEDOT PSS graphene oxide exhibited higher selectivity towards SO2. Then the next important parameter is repeatability. So the repeatability of the PEDOT PSS graphene oxide sensor was tested at 10 ppm with repetitive cycles. So all these 3 times the gas sensor is highly repeatable, which indicates that its application is real-time application. And then finally we hello. Yeah, and then this is the calibration curve for the different concentration of SO2, and we got the linear response as the concentration of SO2 gases increases. So this is overall. So I will conclude my talk here. Like we have seen, there is growing interest in gas sensor and biosensor due to its huge application in various fields. Then we have also seen the technique for device fabrication, that is photolithography process, and the alternative is like iron etching. So with this, I would like to acknowledge my university where I have done this all research work, Rusa Center for Advanced Sensor Technology, Dr. Babasaheb Ambedkar Marathwada University. Then I worked on the SARB project and IUC project also. And last month I was working in Kongon University, Seoul, South Korea. And last month I got the better opportunity and immediately I moved to the United Arab Emirates and now working in American University of Sharjah. So that's it. Thank you for your kind attention. And it's time for question and answer.
Thank you, Dr. Pasha Sayed, sir. Now the session is open for the discussion. If you have any queries and questions, you can ask to Dr. Sayed, sir. The session is open for discussion. I request fellow participants, those who have questions, queries regarding the talk which we have just listened from the Sayed sir, you may please ask the questions. Yes, sir, go ahead. Kherda Umesh Gunskar. Sir, you can ask the question. Sir, please turn on your mic.
Unmute yourself and you can ask the question.
Gunskar, sir.
Sir, sound problem is created at a moment.
Sir, all of you are unmuted. Unmute yourself because I think.
Sir, one question is posted in the chat group. I
Okay.
can read out the question. The question is, can you explain the detection of diabetes using gas sensors?
Yeah, sure. So, as I explained, this gas sensor field is continuously increasing. So, like when we exhale in our breath, there are many kinds of gases and they are particularly associated with the particular disease. For example, if I am having diabetes, generally we call in India the sugar. So if I measure the acetone level in the diabetes patient and acetone level in the healthy patient, so I will definitely see there is huge difference between the diabetes patient and healthy patients. So from that kind of sensing, we can use this gas sensor for diabetes analysis or breath analysis for this particular of type.
Any more questions?
Hello, sir.
If anyone is like still more information like
Yes.
about PhD doctoral study in American University of Sharjah here in United Arab Emirates, Dr. K. Shetty sir is having my WhatsApp number and email detail also. So I request all students, if those are interested to pursue doctoral study, they can just reach out to me. I will give the detailed information on what are the requirements, what is IELTS score, whether you have to go for GRE or not, and what kind of requirement is there. So you can reach out to me if you wanted to. Yeah.
I will provide your email ID. Sir.
Yeah, sure, sir.
Shall I provide your email ID?
Sure, to everyone, sir. No problem.
Okay.
Yeah.
So yes, sir. I
Okay.
think
Yes.
Thank you.
Mr. Kachwe is having some question.
Okay.
Yes, sir. Thank you for your informative lecture, sir. One small doubt is to me that
Yeah,
you
sure.
didn't mention anything about the temperature in your all presentation. So my question is, whatever sensors you have created or developed, all sensors are working on room temperature or they are working at some different temperature? What is the temperature
Yes.
parameter?
Yeah. All are operating on room temperature.
Okay, thank you, sir.
One more question was there, Pashaji,
Yeah, sure, sir.
posted here.
So the question is, are vitamins can be detected by the gas sensor? This is the question posted in chat.
Vitamins
I
like
mean, in the
what
sense
kind of
deficiency. Deficiency.
vitamin deficiency? Like it is hard to say, but we can see maybe this vitamin or if it is biological entity, then we can develop the biosensor. So kind of biosensor we can develop so that using biosensor we can detect vitamin also. There are two kinds of detection. Like the first is like just you have take out the sample from the body and then analyze in the laboratory. And second is on body measurement. So it depends on what kind of sensor we are working. If we will do this kind of research, then it is possible. Yeah.
Thank you, sir.
Thank you, Pashaji, for your informative lecture. Thank you very much on behalf of our college.
Yeah, and thank you so much for inviting.
It was very nice to see you online.
Yeah. I
We'll
am
meet
also very happy.
sometime when you happen to come to India.
Yeah, sure. I will come and
Thank
visit
you. Thank you very much for accepting our invitation and coming online and delivering a very nice talk. Thank
Okay,
you.
sir. Okay. Yeah, thank you.
Thank you once again, Dr. Pasha Said, sir, for very nicely explaining and exploring sensors and their applications. Now I request Dr. Yemakar sir to propose the vote of thanks for this session. Yemakar.
Thank you, Kalamchi sir. distinguished guest and esteemed speaker, and all participants. As we conclude the first session of Dr. Pasha Sayed sir, who have illuminated us with his presentation on functional nanomaterials for advanced sensing devices applications. It is my honor to extend a heartfelt note of gratitude to all who have made this session a resounding success. First and foremost, I would like to express our deepest appreciation to Dr. Pasha Sayed sir for sharing his expertise and insight with us today. Your comprehensive exploration of functional nanomaterials has not only enriched our understanding but also opened new horizon for research and innovation in the field of advanced sensing devices. A special mention goes to our distinguished and participant who have attended this session. Your active engagement and throughout provoking question have contributed significantly to the depth and richness of today's discussion. As we reflect on the insight gained during this session, let us carry forward the spirit of inquiry and collaboration that defines the search of scientific excellence. Together, we have the power to drive meaningful change and shape the futures of sensing device technology. Once again, thank you to everyone who have played a part in making this session a success. May the knowledge gained today inspire us to continue our quest for innovation and discovery. Thank you, one and all. Over to Kadamse sir.
Thank you, Vinolkar sir. Now, immediately we are going to start the second invited talk. It's a guest, Dr. Gangadhar Banapannawar sir. Okay, we are joined. Sir, can
Yes,
you-
sir. Yeah. I'm audible?
Yes.
Okay, sir. Yeah.
Sir, are you ready for the presentation?
Yeah, sure. I'm ready.
Please share your screen.
Okay.
So the next talk will be delivered by now the Dr. Gangadhar Banapannawar sir, who is postdoctoral research associate, Department of Physics, Durham University, United Kingdom. Now I request Dr. G.B. Gundlewar sir to briefly introduce our next speaker. Dr. Gundlewar sir.
Thank you, Dr. Kadamse sir. A very good afternoon to all of you, ladies and gentlemen. I am honored to be here to introduce our distinguished speaker for this session, Dr. Gangadhar Banapannawar sir, who is postdoctoral research associate, Department of Physics, Durham University, United Kingdom. Currently, Banapannawar sir is working as postdoctoral research associate in the Department of Physics, Durham University, United Kingdom. He has also worked as research associate, Department of Physics, Indian Institute of Technology, Bombay, India during 2022 to 2023. He completed his Master of Science in Physics from Department of Physics, Karnataka University, Dharwad, India. He completed his doctoral degree, PhD, as an Institute Research Fellow from Department of Physics, Indian Institute of Technology, Bombay in 2022. He was awarded International Travel Grant from Indian Institute of Technology, Bombay in 2022. He has 3 patents on his account. He has published 12 research papers in reputed international journals and presented research papers in many conferences and seminars. With this brief introduction, I request Dr. Gangadhar Banapannawar sir to deliver his talk on organic optoelectronic devices, exciton transport in OLEDs. Dr. Banapannawar sir, please.
Thank you, sir.
Sir,
Thank you,
have
Surendra sir.
1 hour.
Okay.
And you can keep reserve last 10 minutes for the question.
Sure. Yeah.
Go ahead.
Thank you, Surendra sir, for the kind introduction. Thank you, organizer, for giving this opportunity to present and share my thoughts and data here with all of you. So let me start with, today I'm going to talk on mostly about the organic semiconductors, how these are actually we call as semiconductors, what is the, how these we can see the conduction and kind of these excitons and the transport, and how we use some of the optoelectronics techniques to track some of these excitons in the semiconductor devices. So the outline of today's talk is I will start with some background to the organic semiconductor and exciton transport, and what are the methodology we used to study these triplet exciton. I will come to that point, what is this triplet and why we used, why we focused on this one. And I will just flash some of the work I did on some small molecular OLEDs, and I will conclude my talk. So the organic semiconductors, we know the semiconductors already. So the property of these materials, especially the electronic properties, stay in between like conductor and the insulators. So these are the semiconductors, solid materials, but organic. That's also we know the hydrocarbons, what we generally know these metals. So overall, this makes a new class of material. So these are mainly made up of hydrogen and carbons, and there will be some atoms such as sulfur, oxygen, nitrogen, and these materials have ability to absorb the light, conduct the electricity, and emit the light together. So overall, all these property makes them a promising candidate for the optoelectronic devices where this light and the current is involved together. The main advantage about this material is we can tailor its band gap and structural properties and everything. And these are having a very good solubility in all most of the solvents. And since these are a kind of hydrocarbon, what I said, the hydrocarbons, like our body tissues are all made up of hydrocarbons. So similarly, these materials can be used as a flexible and transparent devices things, and which is really difficult in terms of like whatever the crystalline family we see, the inorganic semiconductors. And the main, like if I want to mention where exactly these applications are, like in LEDs, lasers, field effect transistors, detectors, solar cell, and many more. And these are the like a few of main commercially applicable sectors where we can use these organic semiconductors. And one of the other highlight is actually these are a solution processable, like if you are talking in or inorganic, the silicon gallium based, so the fabrication techniques are really complicated and expensive. So in that point of view, if I'm talking, these are solution like very simple, like a printing processes we can use. And of course vacuum based also possible, so I will come through like in the later, like how exactly we can use all these things. And we go the three scientists actually awarded Nobel Prize to the development and discovery of this this class of material in 2000. Actually, this discovery happens in 1970s, and they awarded Nobel in around 2000 for this particular polymer I mentioned, shown here. I will come to next, like how these conduction happens in these materials. So as I mentioned already, so these are hydrocarbons and having the best property in terms of light, flexible, and low cost technology. Because whatever the process we use to synthesize these, like fabricate the devices using this material is very simple, like just using the solution in even in the lab scale or even in the industry level. So the fabrication techniques are really cheap as compared to the inorganic materials. And all this manufacturing or even the synthesis, but after the synthesis, if I say about the fabrication of the devices, like whatever the device I mentioned, LED, solar cell, detectors, and everything, these are all happens at very low temperature, like hardly 100 to 100 degrees Celsius, because whatever the temperature we need is just to operate the solvents there. So this small temperature is enough, but in term of the inorganic, it's like in some I can say like 1000 degrees Celsius. And we can use a simple printable solution and vacuum processing for the fabrication purpose. And very importantly, these are all biodegradable because it's just a hydrocarbon. Some of the like you can see the commercial applications where we can use this material for laser sensing, solar cells, and many more. And you can see some of the pictures where we can we already see this organic LEDs in our mobile displays. So like if you see from last few years, like especially the Samsung in India is coming with OLED displays. And there are many, I will show in the next slide also, the commercial TVs and all, which are transparent, flexible, foldable, and all these things can possible when this active material, the semiconductor, is thin enough and flexible also. So especially because I'm going to focus only on the mainly LED here, because of course there are solar cell detectors and everything, but my research work mainly align with the LEDs display technology. So I'm going to focus mostly these all material, how we are going to use it in a LED, and how we, whatever the device physics and everything. So as compared to the LCD that's used to come before, so LCD always have liquid crystal displays, always have a backlight on, so that covers the complete visible light. And so there will be a liquid crystals next to that, so the light will be on always. So if for example there is in the displays we have a pixels, right? So green, blue, red, and all. So according to these combinations we can generate the complete visible spectrum. But consider within this figure, at this particular point I have only red. So at this place I need only red pixels to be on, so I don't need a blue and green. But in term of LCD, so the whole light will be on. You will have a blue, green, red, everything, but you will block the remaining colors to see the red. Means we are actually wasting the energy here. So that can be solved in LEDs. So of course it comes in the in inorganic also, but as compared to inorganic, there are some advantages in the OLEDs. But in terms of just LED, if I'm saying, there is no backlight needed here. So there itself, we are going to save a lot of energy. So these are very less energy consumption devices as compared to the our old LCD technology. So along with this thinner and very efficient, we can see excellent viewing angle. So in the LCD devices, the viewing angle is hardly like I think it's reported around 80 degrees. So but in the LCDs, in the LEDs, it can go up to 160 degrees. Means you can see the screen or displays in any angle also, so the image will be same. So that's the good property of this LEDs as compared to LCDs. And since we have a color tuning property for these materials, like you can tune the color from UV to near IR by changing some of its molecular structures and everything. So the tuning of color is quite easy for these materials. So you can see some of the commercially already available the light emitting diodes of the organic materials. Like this you can already see in some of the halls. You can see this the flat panels, the white light emitting diodes, and LED foldable flexible display, and Samsung, and this is a curved display, and the flexible LG OLED TV. So these are some of the commercial examples where I'm say this organic LED is used. And let's go to some understand its electronic structure. I'll say that it's a semiconductor, but how it becomes a semiconductor, how it is actually conducting the electricity. So in hydrocarbons, we see that this hybridization, like sp2 sp3 hybridization. So accordingly we will get a single bond, double bond, or triple bonds. So I'm going to focus on only sp2 hybridization. In this particular sp2 hybridization, so what happens, the four valence sorry, one second, so my voice is actually going here. Am I audible now? Hello?
Yes.
Okay, thank you.
परभणीचं आहे शिवाजी कॉलेज.
So in the in sp2 hybridization, so these four valence of the carbons undergoes the molecular hybridization and forms a these three sp2 hybridized orbitals and one unhybridized. So hybridized.
Gangadhar sir, you can please unmute yourself.
Oh, sorry.
Yes.
I'm hearing a lot of background sound. Oh, and now it's correct. Yeah. So that one Z-plane orbital is forming the pi bond. So this is the main concern here because the sigma bond is very strong as compared to the pi bond. This is already we studied in organic chemistry. So but after this pi bond formation, so there will be bonding and anti-bonding formations and all. So that we, one second, it's yeah. So here the ground state bonding, the molecular orbital we call a LUMO, that is lowest unoccupied molecular orbital, that is the excited state. The HOMO is the highest occupied molecular orbital, because in the ground state, at the normal condition, like before excitation, we can see all the electrons are staying in the ground state. That's we call them the highest molecular orbital. So whatever the deeper energy levels, that is not in our concern, because so that you can see here, like in a single molecule, for example, just in ethane, because when I say it's the sp2 hybridization, so we see the only the double bond here. Okay, there is no single or third bond that comes in a sp and sp3 hybridization. So in just sp2, we can see the organic molecules which are having either single or double bonds. So in this kind of materials, so the whatever the energy state we see, so if the molecule is isolated, a single molecule, you can see a single the energy level for ground state and excited state. But when I start combining, that's what we see in the band theory. So when the more and more atoms are coming together, so the interaction between them makes them the energy level split into 2, 3, and so on, according to the whatever the environment it has. So here the same thing happens here. So when I'm making the chain length longer, so here two molecules, and I just keep adding the carbon atoms, so I can see the splitting of its energy levels, and the single becomes double and keep on going, because in finally whenever we see the solid, it's not a single molecule, it's a bunch of molecules. So, and that also I'm talking about the chain length also. Here the single ethane, but I'm going to add the carbons, the ethane together. So when it becomes N, means the ethane number is actually adding together and goes to like large number. At that case, the splitting becomes so small, and it finally a band. That band we call now HOMOs and LUMOs. So what? But this is in general I'm talking. But the conjugated polymers are the one we need to use it as a semiconductor. So conjugation, that is actually the alternate single and double bonds. Okay, why we need? Because all double bonds are not possible, like because the valence is 4, so we cannot have a 4 all together. So but the single and double bond, that should be alternate. That's called the conjugation. For example, we saw these things in the benzene, where this double bond can be anywhere between these 6, right? That's why we write it as a kind of just circle or dotted. That indicates the whatever the electron involved in these double bonds, that is the pi bond, is actually delocalized over the complete ring. It is not stay at single carbon, because the electron involved in sigma is actually a very localized, means that is actually stay at that particular carbon atom. But the electron present in the pi bond, so that is a delocalized. That's what we want, because I'm talking about the current, electricity, it's a flow of charge, right? So the electron should move, but in the inorganic it's completely different, because in metallic or in the semiconductors, whatever we have, the electron we see, intrinsic or extrinsic, is a mostly free, because the interaction between positive the atom and the valence electron is so less, means it can move almost freely. So, but in this case, it's not the, but in organic, it's completely different, because this pi electron is, of course, movable, like it's within the ring, right? So whatever because it can be travel these within these 6 carbon atom, but that's fine. At least it's not stayed single atom. That's what we call a delocalization. So, like for example, you can see how the conjugation, like in this particular, it's a polymer. It's N, means this unit is completely following the same trend. Like you can see the alternate positive and single and double bonds. That's what we need for the delocalization. What we see here means that electron can travel from here to here. Means that electron wave function is present complete over this complete molecule. If that is a chain, of course, it goes to the other end of the chain now. So, but in term of the other molecule, you can see the break of the conjugation. There is a double bond, but the single, after that again it is a single. Means electron can be delocalized within this small region. So if I want this electron to move to the other end, it's not possible, because there is a breakage of the conjugation here. This is so. So finally, when I'm saying this organic semiconductor, so I'm talking about this only the conjugated polymer here. So we can see the pictorial representation how this actually electron is just moving from here to here just by flipping the double bond to the other side. And some of the polymers you can see here, like this is like a small molecule, but if I use this monomer in a repeating units, so I can make a like varieties of these kind of different molecules, and these are all, we can say, like a kind of polymer where my monomer is having a repeated unit. And of course, this is again a single molecule, iridium complex. So along with the hydrogen and carbon, so I have a iridium metal complex and the nitrogen and all these things. So this is the phosphorescence material. I will come again later. This is the PFO, the one I mostly used in my research, which is a LED material. This emits a blue light. And so a small change in its side chain can make it to green. That's what I'm saying, the color tuning. So some of the optoelectronic devices, the like FETs and the LEDs, these are the other possible devices. So in the fabrication, what I mentioned, the solution process fabrication technique. So there are varieties of fabrication we can use for this one. The first one is a simple spin coating.
सध्याला एक सेट तर द्या ते मॅडमला पाहिजे एक.
So in spin coating, what happens? Just I dissolve this organic semiconductor in some of the solvents where this have a very good solubility. For example, the xylene and dichloromethane, all those things. So I make a solution out of it, and it is completely dissolved. So just drop 1 or 2 drop on this substrate, whatever the substrate we use, like a glass or plastic and whatever. So and just spin it for 1000 or 2000 RPM speed. Now what happens, since this material is so thin and solution completely soluble, it can make a uniform film, and just after annealing the solvent you will get a very uniform thin film. That's just simple as like, but it's mostly for the laboratory scale. But if I'm talking about for a commercial or industry level, so the printing technique is the best one. So I will make a, for example, devices, it'll have a multiple layers, right? So there is, what I'm saying is the organic is a main active material, but along with that, I will have a lot of other interlays to electrodes and the electron and hole injection layers and everything. So there will be a multiple stack of these layers, maybe organic or inorganic together. So you can just make a solution of all these materials. I can say it's ink, for example, and you can just print it as a newspaper. So there is a printing technique, a specific printer for these things. And whatever the pattern you need, you are just printing one by one layer, and at the end you will have a device. So, and another is the very clean evaporation technique. So here what happens, just if the material is not polymer, because polymer will have a repeating unit for like thousands and all, so that's a heavy molecule. It cannot be evaporate at these low temperatures. So but if I'm talking about the monomer, a small molecule, that can be sublimate, and you can use it in the evaporation technique. So some of that the materials can be used in an operation process also, mostly the small molecules, where you will have in a vacuum chamber. And once you heat the material, it will get evaporate and sit on the substrate. So if you have the multiple source like this, like for the different layers, and you are depositing one by one, even the device will be ready. And any of these techniques, either, excuse me. Yeah. So any of the technique, whatever it is, printing or evaporation based. So finally, what you can use it in is a roll-to-roll fabrication. For example, in inorganic, what happens? So your panel size will be fixed. I'm not saying a panel because it's all the cell adding together, but a single cell, maybe it's 1 meter square or something. So that is the limitation. So every time you can make only that size device. But here in case of organics, since this is flexible and very thin, so you can fabricate in a roll to roll, because you have a roll of substrate. So that roll is actually opening up, and you are, like, for example, like this is a roll of plastic substrate, the transparent, and the roll is open up and comes, and you are printing all the layer one by one. At the end, after fabrication, you no need to just keep it flat, and you can roll it again, roll it back for the transport later. So that's the advantage, means within a small area, so you can fabricate it like for a meters. So if I compare this overall, like in with the inorganic, for example, the silicon. So what are the main changes? Like in a commercial level, if I'm talking, the cost of fabrication of, for example, I will just take maybe LED or solar cell, whatever. The cost of that the 1 feet square device, the cost is this much different. For organic, it is just a £5, the dollars, and whereas in inorganic, it's 100. It's not just about the material, or like the silicon or organic is cheaper or something, but it's complete fabrication technique, the manufacturing technique. Because you can see the fabrication cost is, like, if you want to set up a the capital for that, the industry for that. So for the organic, it's a very low budget, because whatever you need, the hardly like some the whatever the inkjet printers and all those things, and it no need put a lot of conditions for that. But in terms of inorganic, it's a big capital business. In the device size, of course, in the inorganic, it's like less than 1 meter square. Of course, this is the maximum. But whatever you see in the commercial silicon sonar, that is a panel. But within the panel, whatever the cell you have, that is well less than the 1 meter square. But whereas in organic, you can make it like in one dimension, maybe some meter or feet. But in the other direction, in the Y direction, it is just a roll. You can just make it as big as you want. And the substrate in the inorganic, it mostly the glass we need, or the metal. But in the organic, you can use in a flexible also. And the organic is okay to fabricate just in the ambient condition. You just need 100-200 degrees Celsius and just a normal the fabrication room. But whereas in inorganic, we need a ultra clean room. And the processing is solution based. Here it is multiple photolithography. This is the point where this cost and everything makes a huge difference. So I will come to the next point, where what I mentioned in the head title also, the exciton. What exactly is this? So, and how we are going to study this one. So the Coulomb's law, we know that the force of attraction or repulsion between the two charges is proportional to Q1 and Q2, and it's inversely proportional to the distance. And the another important factor, that is the epsilon r. So the dielectric constant. So the dielectric constant of the inorganic molecule, that is the crystalline materials, it's around in the range of 10 to 15. But whereas for the organic materials, it is 2 to 4. This is the main difference between these two materials, because once the epsilon r is smaller, so you can see the F is maximum. So it's inversely proportional. So hence, because of this change in the dielectric constant, the crystalline, the inorganic materials forms a exciton that is called the van der Moot exciton. Here, once the electron is the escape from the material, the force of attraction between this positive hole and the negative electron is so weak, so it can travel to a longer distance. This is for example, exciton radius. If I'm saying, this is actually bigger, so it's extend to the many atomic size. So the binding energy is less than 25 MeV. The milli electron 25 MeV is almost like a room temperature thermal energy. At 300 Kelvin, the room temperature thermal energy is almost 25 MeV. So that small thermal energy present in the environment is enough to separate this hole and electron. But that is not the case in molecules, in the organic, because the binding energy is almost like a 0.2 eV, means around 200 MeV. So it's even more than that in some materials. So it's around, as compared to thermal energy, it is so high, so it is not easy to separate at room conditions. So they, of course, we need some of the external factors to separate these electron and holes. So and these materials are mostly crystalline, the inorganics, but these are mostly amorphous. There are some molecules, the small molecules, we can see a small range ordering, but overall it's mostly comes under a amorphous material. But we already know that in the amorphous material the conductivity is so poor. But being it amorphous and the conductivity is low, but still how we can actually use this as a optoelectronic devices, that we will see. And you can see the diffusion length, that like once I create like inject an electron or a hole, whatever, so that creates the bind state of electron and hole, the exciton in a single sentence, if I say a bound state of electron and hole. But that is, whereas in a metal or in this inorganic, it's mostly, I can say, a free electron. But in organic, it's a completely bind, the electron and hole are not at all free. Means if they're moving, only electron is not moving, the hole and electron are togetherly moving from one side to other side. So the diffusion length of this exciton in organic is so small, it is just 10 nanometer, whereas in inorganic it's some hundreds to 100 nanometer to a micrometer length. So this small diffusion length is enough actually to make it working in organic optoelectronic devices. So how it diffuse actually, so we will see that. And the type of excitons, there are different classification I can see. For example, like there is a molecule, M is, I'm representing one molecule, whatever the one organic molecule. So once I excite it, so it can create an electron and hole pair, because previously it was all in the ground state. Once I excite the electron to the excited state, now hole is in the ground state and the electron in the excited state, but these two are within the same molecule. So you can see at the other part, like whenever the molecule I'm saying, it's not an element, right? It's a molecule, the big chain, there are multiple hydrocarbons. So one electron will, the excited state electron will stay at one part of the molecule, hole will stay at some other part of the molecule, but within a molecule. So those are called the intramolecular excitons. But in some other cases, we can see once excited, the electron will go to the maybe neighboring molecule. That's called the acceptor, because the previously it was in donor. So once I excite it, the electron will go to the excited state of the donor and transfer to the acceptor. Now, electron and hole are actually at the different molecules. That is called the intermolecular excitons. And there are some cases, for example, what I mentioned previously, these are bound states. But using some factors, if I separate out these to a little bit longer distance, still they are at a very poor interaction, but still these are together. That's called the spatially separated, but this is a very different case and special case. But mostly what we see in organic are these two, the intramolecular or intermolecular. So for example, if I show in this particular molecule, this is called the polyfluorine. Polyfluorine, there are many, but this is the F8BT in simple, I can say. So this is a green emitter material used in the organic LED. So this is a molecule having, you can see like 3 to 4 rings, 3 rings, and the side chain of this CH3 and the nitrogen and sulfur. So this is a single molecule and there is a repeating unit. But within the single molecule, if I excite this one, so what happens, you can see this is the DFT calculations. So this is a side chain, what you see here, that is here. There is no conjugation. This is all a single bond. The spring type what I'm showing is just a 1 CH3. So this is all a single bond. I don't see any conjugation, means I don't see any conduction here. But at this point, it's all alternating single and double bonds. So within this main chain, when I excite it, the HOMO, the ground state, will stay mostly at this point, but my excited state will move here. That you can see here, the LUMO is at this point and HOMO is here. Means the hole will mostly delocalized within these two. My electron is mostly delocalized here. Means both electron and hole are within a same molecule. So this is the intramolecular, but inter is like when the electron is jumped to the neighboring molecule. So and another kind of classification, this is what we see is in a spatial way, like it's in the same molecule or different. But if I'm being more specific, in term of it's a spin. Okay, so in the ground state, it's an anti-parallel, right? So when excited, the ground state might be parallel or anti-parallel. If the spins of the electron and hole is in anti-parallel, that's called the singlet. And if it is in a parallel, that's called the triplet. So accordingly, this one, the spin multiplicity becomes 1 and 3. Means for us, every one single state, I have a 3 triplets. So that's the big difference here. That's how the efficiency actually controlled by these two factors. So in a Jablonski diagram, in a simple auto, if I see what all the transitions, so this is the ground state, that is the S0 we call, because that is a singlet ground state, that is the HOMO. But since the spins are in anti-parallel, so I just call it as a singlet ground state, S0. In excited state, it's an anti-parallel again, but the another electron is at the excited, that's called S1. And the triplet, so whatever I see previously, the parallel spin of the spin combination triplets don't having any ground state. There is no T naught possible, because if the electron and hole are staying together, they cannot stay parallel. They will be anti-parallel always. That's why there is no T naught exist. So once excited, so it goes to the higher excited state. So since this is a spin allowed, right? So this is also down and this is also down. So it can come down anytime. So it will give the fluorescence. This is where we get the emission. But by chance, if it comes to here because of, the intersystem, this is called the intersystem crossing because of spin orbit coupling. So, but this emission is really generally not possible. But in some cases, we call a phosphorescence, like when material is doped with some heavy atoms. In those cases, we can get the phosphorescence. So otherwise, these triplets are a non-emissive. But in electrically exciting, if I inject the charge carriers, so the spin multiplicity is 1 here and 3 here, means 25% are the singlet, the remaining 75 are triplets. So means 75% of the triplets are not giving any emission, only in phosphorescence, but otherwise it will not give any emission. Means we are losing 75% of the energy. So we have to utilize the triplets. This is the where I can highlight the triplets are non-emissive, but really important to consider, so that we have to study this triplet, especially so that how we can use it. So somehow we can have to use these techniques to convert this triplet into singlet. So this is the energy at lower energy. So we need some energy, or I will show that. So we have to convert this triplet into singlet. So there are, so I will just skip it. It's not much important. So I will say this, how this exciton are actually transporting. So once I create this hole and electron, so it will start diffusing. So next to one molecule to another molecule, it's called the hopping. It's not a free charge transport, it's a hopping mechanism. Means a molecule is there, exciton is there in one molecule. If it want to go to the next molecule, it has to together get the energy from environment or thermal energy and move to the next one. Every time it jumping from one molecule to other molecule, it will acquire the energy. It needs energy to jump. That's called the hopping. So once it generates, and before recombine it to the ground state or get quenched at the interface and all those things, so whatever the distance, it can the diffusion. So how it is moving, the singlet is moving differently, and the triplets, you can see pictorial diagram here. Though in the singlet, this is the anti-parallel combination. Here the one molecule to another molecule is, there is no exchange of charge carriers, it's only exchange of the energy. Means this molecule will transfer energy to the next molecule, but electron will stay here only. But once it transfer, this electron comes to ground state, and this will get excited, that you can see in the final state. This is how transport happens in the singlet. But in the triplets, is a dexter, means there is no energy transfer, there is a transfer of electron between the molecules itself. Means at the excited, electron will go to the next one, and at the ground state, the another electron will come back to the previous molecule. So there is a physical exchange between the electrons here in term of triplets. So in the organic, how these triplet and singlet are actually playing the role. So in a typical, this is a general structure of organic LEDs. We have a like emissive layer. This is the blue one. You can see it's a main organic, where this light the converts into light. So the working principle is, once I inject the holes and electron from the anode and cathode, it transport through the device stack. Once they meet at emissive layer, they form the exciton. This is the bind state of electron hole. Once they recombine, that gives the light. So the efficiency of this one, like how much charge I'm injected and how much light I got outside. So that depends on multiple factors. That is the charge balance, like how is the electron and holes are in equal number or not, and the PLQ, either how good PLQ is, photoluminescence quantum yield, how good my material is to emit the light, like all radiatively. And the singlet to generation ratio, that's what I mentioned, it's just 25% generally. And outcoupling efficiency, once the light is generated inside, and how much is get escaped, because there is multiple interfaces. So there is total internal reflection, self-absorption and everything. How much light comes out, that's called the external quantum efficiency. But if I remove this coupling, the whatever the remaining three factors represents the internal quantum efficiency. So during this one, I can maximize the first two, but the next two is the biggest issue. But outcoupling is again a big challenge. But anyway, people raised it 20 to like up to 50. But the big loss is here, the singlet generation ratio. So we have to use that remaining 75% of the triplets, and there are multiple attempts for that, like how to utilize the triplets. The in the simple fluorescence, it is just a 25%, but in the phosphorescence, that if I dope a heavy metal, that is mostly iridium and platinum, so I can make the triplet into radiative recombination, means I can flip the spin and comes to the ground state and gives the emission. So that's possible, but here, since the heavy metals are very limited and this becomes very expensive, and the very recent one is actually the thermally activated delayed fluorescence, means using some techniques, I can make the molecule such a way that the gap between singlet and triplet is so small, means my thermal energy 25 MeV is enough to bring it back. So the reverse intersystem crossing can happen, and I will populate all my triplets into the singlet, and from the singlet you will get the emission. So this is one of the technique, and the other technique is triplet annihilation, means two triplet can combine and gives to the one singlet. So this is the one molecule I'm going to study I will show some of the data related to this one. So how we are tracking. So what I mentioned previously, this triplet, why I will till now I will mention like why triplets are important, even though these are not giving light, but they are actually the main reason to limit the internal quantum efficiency just to 25%. So we have to utilize the triplets. So it's very important to study the triplets first. So this is the way we actually use this particular molecule. Actually, this molecule is actually the TTA based triplet annihilation. In this particular F8BT, so the two triplets will combine and gives one singlet. Of course, we are losing one triplet here, but at least we are converting that one triplet into the one singlet. So in this one, why this particular molecule? Because this molecule is actually known from like 2005. There are many research papers in 2020. So you can see this molecule gives the good LED even at 1 micrometer thick. Otherwise, generally these molecules will work hardly 100 to 200 nanometer thickness of the layer, because its conductivity is so poor. So we cannot use a 1 micrometer thick layer, but this particular material is actually efficient up to that much thickness. So that is the curiosity we came across, like why this particular molecule is working so nice at such a high thickness. So you can see in a time resolved emission. So this is the where we can get the very fast emission at very earlier, like 10 nanosecond, that is from the singlet. But whatever the emission you are getting here, that's all from the TTA, means triplets are converting it to singlet and gives the emission. That's why they are coming like some 100 of nanosecond to like microseconds. So we are going to focus on this particular region because this is all singlet that we don't need, and this is the where the TTA is happening. So we wanted to study the triplets transport at this time scales. So we use that particular the device structure to study that. So how exactly we are combining these things are, like, consider this is the general structure of the devices, and the light is emitting from the organic material somewhere here. So how much light is coming out, that depends on what are the layers in between, what is the thickness of those layers, what is the optical constants, and the position of the emission and everything. So whatever you see outside, that reflects completely the position from where the emission is coming. Of course, from where the emission is coming, where my triplets are. Okay, those triplets converted at singlet that position and gives the emission. So this is where we are going to connect these two, like what you see outside that actually reflects from where it is coming. So using the optical model, so we actually simulated so how the emission looks like outside, the angular pattern, and how it is related inside. So that's what we see. For example, here the normalized outcoupling, like whatever the light is coming out is a function of MO2 thickness, like whatever the one interlayer we used, or the recombination zone. Means I can, like in a simulation, I can change the thickness of the layer, or I can change the position of the exciton. So by changing these things, what we see is a variation of its outcoupling. That what we can see here. So this is the point we connected the position versus outcoupling. So experimentally, this is how we measured. This is a device. We excited the pulse voltage, and whatever the emission is coming, that emission measured in all the angles, like from 0 to 90 degree. This is how it looks like. It's mostly Lambertian. So, but when I measure this emission pattern at a different time delays, we can see a small change. Like it's a very small. What you see here previously also, it's like you can see like just 1% to it's just a 0.94. So that's the small change we can observe outside. So we need a very sensitive detector for that. So using that we detected, and we using the optical model, using simulation and our experimental data, we extracted with respect to time how my triplet location is changing within the device. So from this one, and using simple diffusion equation, the L is actually the position within device, and the time we are measuring. From that we can calculate the dt, that is the diffusion coefficient of the triplets. That's what we needed, so that how fast the triplet is moving. So we conducted this one for the different thickness, because we observe with the thickness its efficiency is changing. That's the main target. So what we see is the triplet diffusion coefficient is enhanced from 9 into 10 raised to minus 4 to 2 into 10 raised to minus 3 centimeters square per second. So I will tell you why it is increased. So this is one technique, and the other technique is a simple PL imaging. That is, there is a thin film. So once I excite, here is the thin film sample, and this is all the microscope I'm using. So once I excite the sample using microscope objective, means my spot size is so small, like it's like a 200 to 300 nanometer radius. So I excite it. So this is the laser spot you can see, and I will use the gated ICCD. Means this is a spectrometer. You can measure the image or the spectrum at a different time delays. So initially it is just a laser, a small spot, but you excited the material to a small spot, only this much region. But over the time, you can see spot size is growing. Why this spot size becomes bigger? It is just because of its diffusion of the excitons. So if I capture the images at different delays, like 100, 600, and 1000 nanosecond, so the spot size is getting bigger. So how fast it is growing with time, that gives the diffusion. For example, time versus change in its the mean square displacement of the spot size will give the d value. So so what we observe is, by increasing the thickness of this polymer, what we observe is the triplet diffusion coefficient is actually increasing. So why it is increasing? To see that, we did some of the spectroscopic studies, that is photodeflection spectroscopy, PL, and Sachs measurement. Photodeflection is to measure the tail state absorption. So in ideal semiconductor, what we say, like if it is direct band gap, we can see there should be a short drop. But of course, ideally that is not the case. In real, we have always a tail states, either in inorganic, organic, wherever. So these tail states represents the defects. How good is the material? If my material is perfect, then I don't see any tail state. But why tail states are coming? There is a disorder in the materials. But these tail states cannot be probed with a simple emission or absorption spectroscopy, because the density of these states are so poor, it is difficult to probe. For that, we use the photodeflection. Means whatever the once you excite these from ground state to excited state within this tail part, so whatever the small non-radiative decays are there, that emits a small light, the heat, we are detecting that heat using this particular technique. So from that technique, we can calculate the Ubark energy. That Ubark energy represents the tail state. If Ubark energy is more, means it is a more disorder. So that's what we see here. So by increasing the thickness of this material, my Ubark energy, that is responsible for my disorder, it is changing from 100 to 65 MeVs. That represents by increasing its thickness of the film, material is getting more order. That's what you can see even in the emission also. So if the emission is more order means what? The emission, the PL spectrum will be more narrower. That's what we observe even in the PL, and the Sachs measurement is small angle X-ray scattering represents the packing of the material. If material have some aggregations, you will get the X-ray scattering. That's what we even observe. At a very thin, there is no X-ray scattering, means there is no kind of a molecular aggregations. There is no packing, means there is no orderness at all. But at the higher thicknesses, we can see multiple X-ray scattering that represents the this scattering of the the polymer packing within the thin film. So that's what I want to summarize, like how it is actually different. Means within this particular material, the FHBT, by increasing the thickness, what I can see in the schematic here, at the very thin, maybe the chains, these are actually the yellow one, you can see the molecular chains. Okay, so the aggregation, the molecular chains are mostly random, but there are only some places where these are actually aligning perfectly. So that's what you can see here in this structure, why this alignment is very important. If my chain is very straight, you can see the perfect band, means my electron can travel easily. But whenever I see the this chain is bending or twisting, that's a kind of defect that creates a small trap here. Means electron will trap in this one. If it want to go back again, it needs again some extra energy. So that's how actually it's the diffusion or the conductivity will reduce. So we need a straight, very aligned chain, and the packing also. For example, what this packing I'm talking about, these are the two chains. This is one different chain and the other chain. The gap between these two chains and how nicely these are aligned, that's also important. If these are not aligned and packed perfectly, so that will leads to a potential barrier. So means if the electron want to hop from here to here, so there is a potential barrier. So this needs energy, or it has to tunnel through this one to travel, to transport through this one. So that's why it's very important to keep the straight chain, aligned chain, and having a good packing between the chains. So that's what we see here also, using all whatever the structure and those studies. So by increasing the FHBT thickness, the polymer thickness of the film, so what we observe is the material is getting more order, the packing is getting increased. That's what we concluded from this work. And apart from this one, so this is all a solution based devices. So later what we did, like in our group, actually this is the one patent we filed about this system. This is the system we used to fabricate the devices for a small molecules, like the where I see mentioned the evaporation based. So solution process. So there are already chambers available for a single materials and all those things, but this is the homemade that designed in IIT Bombay and the industry partner with Excel Instrument Mumbai. So multi-chamber system where we have all systems are connected together and connected to Globox again. So where we can actually dedicate a single chamber to deposit one kind of material. This is hole injection, emissive, electron injection, and electrodes. So whatever all these different layers we have, each layer is deposited at different chambers and transferred through a simple central chamber. Means once you put the substrate inside, so it will transfer within the vacuum between all these chambers, and once the deposition done, then you can take it out through the Globox, and it is a contamination free, and it's also gives the vacuum technique so that it becomes a very good technique for the LED fabrication. This is the one, for example, we fabricated in our lab. That is that the TADF. That's what I mentioned previously. Thermally activated delayed fluorescence material, fabricated using that operation system, and we got around like 16% of efficiency for the blue, and of course we have a green and red also. And using this particular system, we deposited the 3-terminal tandem LEDs. Means it is not just a single color. Within a single device, we can make a RGB pixels together. But presently, we made blue and green together. You can see this is all these are the multiple stack layers deposited within the vacuum, like hole injection, transport, and everything. You can see the picture here. This is like the same device. You can see the digital picture here, the top electrode and the transparent electrode and all. So once I connect these two, I will just get the green, and the other one is the blue here. So from blue to green, you can just tune by changing the potential between the change in potential of these two devices. So that's how actually the next generation display will come. So instead of having the RGB in one next to next, now the RGBs will come one upon the above. Means the magnification, the resolution of the display will change 3 times just by replacing the normal classical LEDs with the tandem LEDs. So this is all about some of the work I have done. So I will like to conclude my talk with just overall with whatever the aspects of this organic semiconductor, this like how versatile these are, and we can use in multiple of optoelectronic devices since it has a semiconducting property. It's electronic and optical by combining all together, and of course this becomes eco-friendly because it's a purely hydrocarbons. And since it is a polymer based and the thin film, like we don't need a micrometer thick, since its absorption is so good, emission is so good. So the few nanometers, some hundreds to 100, 10 to 100 nanometers enough. That makes it lightweight and flexible. And it's continuous research on this one makes it more efficient. Like it's almost reaching the solar cell, for example, reaching the commercial, the inorganic based devices. And since it becomes flexible and very thin, you can integrate between your daily life easily. Like you can make a kind of, because this OLED LEDs become one of the promising technique for the for one example I will, the skin cancer, because you can wear it, you can make a cloth out of it, make your device, the LED is itself a simple kind of shirt, so you can just wear it and that gives the light continuously. That's how it can include in your daily life using these particular some interesting features of this material. And some challenges, of course, still working on this one. The scientists are continuously on this one. The efficiency and the stability. Efficiency is somehow okay now. The main issue is with the stability. Stability is not really matching the what inorganic gives, like some 10 years. Of course, the whatever the displays and these are of course showing for some years. But if I come for the solar cells, like the one which is actually outside in outdoors devices, the efficiency is still a problem. So that's where the research is going on. Of course, we'll hope we will find a better solution for that also. So I would like to acknowledge my some of the like professor and collaborator I work with, and my all the colleagues of my previous IIT Bombay and present Durham University colleagues. And during my PhD, we used the materials all purchased from the Cambridge Technology. That's where we got most of the materials, and the DSA for the funding, and NCPRE, which provides all the fabrication techniques in IIT Bombay. So that's all. So I would like to thank all of you for being here. Thank you so much. So now the stage open for discussion. If you have some questions, so
Thank you,
please.
Dr. Gangadhar sir. Now the session is open for discussion.
Thank you very much, Dr. Gangadhar ji.
Thank you, sir. Thank you so much.
Hello. Hello.
Hello.
Hello.
Yeah, I
Can you hear me, Dr. Gangadhar ji?
Yes, I can hear.
Thank you very much for your nice presentation. You are doing nice piece of work, and we are happy to see you in our seminar.
Sure, sir. Sure. Thank you so much for this opportunity to
Thank
share
you
my
very
thoughts
much.
here with all of
It
you.
was a
Thank you
very
so
nice
much.
presentation.
Thank you, sir.
Participants are requested to ask the question. If you have some queries, you can ask to Dr. Gangadhar. Any questions?
याच्यात आले तो.
Or you
Chart
can
मध्ये.
put it in chat also. Anyone from the participant? Please feel free to ask the question. So I think
Yeah.
there are no questions from the participants. So now I request Dr. Yenorkar sir to propose the vote of thanks to Dr. Gangadhar sir.
Thank you, Karamsi sir. As we conclude the second session of Dr. Gangadhar Ganappanwar sir, insightful presentation on organic optoelectronic devices with a specific emphasis on exciton transport in OLEDs. I extend my sincere gratitude to all who have contributed to the success of this enlightening session. First and foremost, I would like to express our heartfelt appreciation to Dr. Gangadhar sir for his illuminating presentation. Your expertise and in-depth analysis of exciton transport in OLEDs have provided us with valuable insight into the particulars of organic optoelectronic devices. A special word of thanks goes to our distinguished guest and participant for their active engagement and insightful contribution to the discussion. Last but not least, I want to thank all the attendees for their attendance and participation in this session. As we reflect on knowledge gained from Dr. Gangadhar sir presentation, let us be inspired to contribute our quest for innovation and advancement in the field of organic optoelectronic devices. Once again, thank you to everyone.
Thank you very much, Gangadhar ji.
Thank you, sir.
Thank you very much.
Thank you, sir. Thanks for this opportunity. Thank you all.
have
Thanks
found
for the
a valuable time. You have given a valuable time despite your busy schedule. Thank you very much.
Thank you, sir. Thank you. Welcome.
Now, we are moving ahead to the third invited talk.
Madam,
The talk will be delivered by Dr. Megha Deshmukh, madam. Madam, are you there?
Yes, sir. I'm here.
Okay.
welcome, madam.
Thank you, sir.
Dr. Megha Deshmukh, madam, will deliver her talk. She is Mary Skłodowska Curie Action Fellow, BSB Technical University, Ostrava, Czech Republic. She will deliver her talk on nanotechnology, the future of green energy. Before her talk, I would like to call Dr. Gundewar sir to introduce our third speaker for this conference.
Madam,
Thank you, Gaurav sir.
Present.
Good afternoon to all of you. It's my honor to introduce our distinguished speaker for this session, Dr. Megha Deshmukh madam from VSB Technical University, Ostrava, Czech Republic. Presently, she is working as Mary Skłodowska Curie Action Fellow at Center for Energy and Environmental Technology, Nanotechnology Center, VSB Technical University, Ostrava, Czech Republic. She completed her PhD from Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, India, in 2018. She worked as postdoctoral researchers in Materials Environmental Lab, Center for Energy and Environmental Technology, Nanotechnology Center, VSB Technical University, Ostrava, Czech Republic. During 2022-23, she held the post of research scientist at Department of Electronic Materials Engineering, Gwangwon University, Republic of Korea. She worked as assistant professor in Department of Electronics, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, and Department of Physics, School of Physical Sciences, Punyashlok Ahilyabai Holkar University, Solapur, India. She received Erasmus Mundus Euphrates Fellowship at the Department of Physical Chemistry, Faculty of Chemistry, Vilnius University, Vilnius, Lithuania, in 2015-16. She is a reviewer for more than 22 international Scopus Index journals. 2 patents are in her account. She is a lifetime member of Iron Beam Society of India. She has a major research collaborations with Professor Arunas Ramanivicius, Faculty of Chemistry, Vilnius University, Lithuania, and Professor Tai Jun Ha, Department of Electronics Material Engineering, Gwangwon University, Republic of Korea. She has published over 45 research papers in international peer-reviewed journals. Her H index on Google Scholar is 16, and on the Web of Science is 18. Over 1170 citations are there on Google Scholar and 1800 citations on Web of Science. She also published 3 books with international publishers and delivered invited lectures in 3 conferences. With this brief introduction, I request Dr. Deshmukh Madam to deliver her invited talk on nanotechnology, the future of green energy. Dr. Deshmukh Madam, please start your talk.
Thank you, Surendra sir, for such a nice introduction. And also, I would like to thank the organizers, the conveners, and co-conveners of the conference for giving me this opportunity to share my thoughts in front of your students and among with you all. As I get to know that the students are like from BSc, MSc, so I wanted to go for something basic or something which can be more interesting for the students also, which can have the essence of research, from what they can understand what does mean the research and how we can go through to these paths to achieve their goals. So I hope this if I could see if this lecture is interesting and my students, whatever students are listening to me, they could get even 1% of this lecture. It will be more great thing for me. So let's start. Yeah. Okay. So is my screen is visible, sir? Hello.
Screen is visible, madam, but it is not
Okay.
full screen. Make it full screen.
Okay. Now?
Okay, now it is good.
Okay.
It is full
Thank you.
screen now, madam. Continue with your talk.
Okay, sir. So my topic of the lecture is nanotechnology, the future of green energy. And yes, if I could give a short introduction about me, myself, Megha, and currently I'm working as a Marie Curie Fellow at the Technical University of Ostrava. And as I told in previously, like with this lecture, I just wanted to go towards to give the essence to the new students with what is the technology and what is the nanotechnology, because we heard this kind of word like nanotechnology of plenty of time, but we don't know what exactly it is and how can we pursue the knowledge with this knowledgeable field, and how can we increase our interest, or we can motivate our students to go towards the research and towards the nanotechnology innovation. So yeah. So nanotechnology, we can say, what is nanotechnology? If we could split this word between nano and technology, then it will be more convenient for us to understand what exactly does nanotechnology means. So nano means the things which are very small, which are very, very tiny, which cannot see those things by our naked eyes. Means if we could say, think about a tip of our finger, and we can place so many things on that this tiny fingertip. So means this very small things in the thing, but the nano, and technology is just incorporating these nano things in the technology to make up for the nanotechnology. Means there is a combination of nano and technology, that is the nanotechnology. Means we are going towards the nanotechnology to unveil the future, different futuristic approaches and different novel approaches like magic. Nanotechnology is doing a magic in nowadays in each and every field. So if we could think about what is nano, the word is basically nano. So nano means what? Making the things smaller, means which we are having those things, making the dimension of that particular thing, particular material at very low dimension. That is nothing but the nano. Means in short, or in a very layman, we can say, like in a very good or just understanding definition, we can say nano is nothing but the making the things smaller and smaller to get the more advantage and more benefit of that particular thing. So nanometer, if we could talk about in case of the scale, so 1 nanometer is nothing but the 10⁻⁹ meter. So if we could take an example of a human ear, like a single human ear is having a diameter of 50 to 70 micrometer, and as we can see by our naked eyes, there's a black wire kind of thing. If we could imagine, if we could see our human ear, but if we could see it under a microscope, here you can see the roughnesses and the humps and the different texture of that particular human hair. This texture we cannot see by our naked eyes. Okay. So if we could take a cross section of a single hair, here we can see the like I have said, like 50 to 70 micrometer diameter of a human hair, and we could take a cross section of that human hair and put multiple of things on the tip of that human hair, like anthra, which are having the different sizes. Like a grain of salt is about 60 micrometer, a dust might waste, it might be about 20 micrometer, a pollen grain about 15 micrometer. Human hair is, if we could take a thickness of this outer shell, it will be about 100 micrometer. Braid mold, it can be about 2 micrometer. Anthrax means the things which are very, very small, the things which can we put on the human hair's cross section. If we could take a cross section, put the thing, these are the objects at micro scale. These are the micro scale. And if we could go further, and if we want to know the comparison between macro, micro, and nano, so just start with the macro scale. Means just from the beginning, we could say macro scale means the things which we can see by our human eye, like a blue whale, which is having the dimensions about 25 meter, a human like about 2 meter, and is about 0.012 meter. Means these things are which we can see easily by our naked eye. That's why these things are called the macro scale. Other one is the micro scale, means where we have limitations to our eyes and we cannot see these things by our naked eyes. We have to go towards the micro scale, means only under the microscope we can see these kind of things. These are like frog egg, human cell, and bacteria. These are about having the dimensions about 1200 micrometer to 1 micrometer. Means these things can be visible only under microscope. That's why we call it as a micro scale. And the third is the nano scale, means those things which are not even visible under micro scale, these are called the nano scale, means whose dimensions are in the nanometer dimensions, like 50 nanometer to 0.1 nanometer, like one atom, DNA, one virus. These things are in the nanometer dimensions, means these things are not even visible by my human eye or not by the light microscope. For this kind of, to visualize these kind of things, these nanoscale materials, we have to go through the electron microscope, means where we are using the electron to see that particular thing as a source of light. So if I want to, if we could go for the example of what nano is exactly means. Suppose consider an earth, and if you consider an earth and a tennis ball compared to this is earth and this is tennis ball, means we can differentiate the dimensions of that two. This is a very big thing and this is a very small thing compared to this big earth. So this is, we can call it as a nano. And if we could take a population of India, means how we are about 100 crore. But if we could take a one person from that total population, we can consider it as a nano. These are the examples just to get an idea what exactly means nano. Nano means very, very, very small or a tiny part of the particular thing. And if next example, if we could have 100 crore, and from 100 crore, you just take 1 rupees among from that 100 crore, you can differentiate that is nothing but the nano, means the things which are very, very smaller. So classification of nanomaterials can be done in different forms, like 0-dimensional nanomaterials, 1-dimensional nanomaterials, 2-dimensional nanomaterial, and 3-dimensional. These are the 4 major categories of the nanomaterial, where we can have the different dimensions for each kind of material, and according to number of dimensions, the identity of that material has been given. So if we could think about the 0-dimensional material, what exactly means by 0-dimensional? 0-dimensional means where length, breadth, and height are confined at a single point. Means we cannot measure the length, breadth, and height of that particular thing. That is nothing but the 0-dimensional. And if we could talk about the nanomaterials which are 0-dimensional, these are nanoparticles, quantum dots, and fullerene. These are the examples of the 0-dimensional nanomaterials. The next is 1-dimensional materials. So 1-dimensional materials was, it has only one parameter, either length, either breadth, or either height. Means we can measure either one parameter among that particular thing, that is nothing but the 1-dimensional. And if we could go for the example of the 1-dimensional material, these are like nanorods, carbon nanotubes, and nanowires are the example of the 1-dimensional nanomaterials. The next is 2-dimensional nanomaterial. 2-dimensional means what? Which has a have only two parameters, either length breadth height or length height. Means two parameters will be present over there. That is called the two-dimensional material. And example of this kind of two-dimensional materials are nanoplates, graphene, and thin films. Three-dimensional materials is the next section. So what is the three-dimensional material? It has all parameters. It will have length, it will have breadth, it will have height. So we can calculate count all these parameters from this thing. So all three dimensions we can measure. That is called as the three-dimensional nanomaterials. So example of three-dimensional nanomaterials are dendrimers, crystals, liposome, nanocrystals. These are some of the kind of nanomaterials which can have all the three dimensions, and these kind of materials are called the three-dimensional nanomaterials. So why small? Why we want to go for the nano? What is the need of this nano thing? Why people are and scientists are so crazy about these nanomaterials? Because why small is very important. Because if we could go through this image here, we can see there is a table. Okay, here is a full shell cluster. There are total number of atoms and surface atom. If we could consider one shell, which is having total number of atoms are about 13, and if we could surface atoms percentage, if we calculate for this particular one shell, it will be about 92. And if we have two shells, means your number of atoms are getting increased, but the surface area is getting decreased. Same happens as we increasing the number of shells up to 7 shells. Here you can say at the last example, 7 shells. I mean, total number of atoms are 1415, but the surface atoms are only 35. Means where the total number of atoms are less, means where we are going towards the lower dimensions. So the lower number of atoms will give the more surface atoms, and these surface atoms will act as your superpower of that particular material to behave in different kind of applications. That's why we need a small material. That's why we want to go for the nanoscale. So the advantages of nanomaterials are like they are faster, lighter, they get into the smaller spaces, they are cheaper in the cost, more energy efficient, and advanced properties at small scale. Means all these small scale materials or these nanoscale materials are superior compared to the macro or micro scale materials. So how we will see how we can how these nanomaterials are better than the bulk material. Suppose this is a bulk material, which is a three-dimensional box, which is having 4 mm by 4 mm meter square area, and this is, if we cut this 4 mm by 4 mm into different pieces, like if, here we can see like 8 pieces. If I cut this box into 8 pieces, here if I could just it a bulk material, here we can see how many dimensions are there, how many sides we can consider here, only 6, like this true, back to 4, 5, and the underneath is 6. Means if could consider this box, its surface to volume ratio, and if you could see the number of sites which is available for the reaction or available for the application, we are having only 6. But if we could cut this box into small pieces, automatically, suppose 2 by 2 mm, automatically the surface area will also get increased. Means where we are having just 6 sides, if we could consider, if we go to the low dimension of this particular box, we'll get the number of sides or number of sides will be get increased. So if I could consider between this bulk and this small dimensional materials, if we could calculate the surface area for this particular box, the surface area will be 96, because if we could consider 4 mm into 4 mm, surface area is equals to height into width into number of sides into number of cubes. So for this particular cube, surface area in millimeter will be 96, but for this number of pieces, it will be about 192. Means automatically the size, if we are going toward the lower size or cutting the particular piece in the particular pieces, its surface area is also increased. The next is the volume. Volume is also same. For this, this bulk material, we can calculate the volume about 64, and if we could go towards the same, it will be 64. But at the surface to volume area to volume ratio, if we could calculate, it will be about 1.5 this bulk material and about 3 for this small kind of materials. Means we are more interested into the surface area to volume area. Means what kind of surface we would achieve after going towards the low dimensions of the material. And here is like eye-opening example. Like if we could consider a bulk material, surface area about 1.5, And if we could go for the low dimensional materials, the surface area is 3. Means as we are going towards the lower side, or we are going towards the low dimensions of the material, we are getting automatically higher surface area. So as surface to volume ratio increases, means these are the hidden sides. Will, if we could, this is a bulk material, this is just bulk material. If we could cut into different parts here, we can also expose the hidden sizes of that material, and we can get the benefit of that particular material. Means if we are going towards the surface, the lower dimensions of the material, the surface to volume ratio will obviously increases. A greater amount of substance comes in contact with the surrounding material, and this results is better catalyst since a greater proportion of material is exposed for the potential reaction. There will be number of reactions we can carry out with this particular kind of materials. So origin, like if we could talk about the properties of these materials, like how bulk materials are different and the nanomaterials are different than the bulk materials. Here we could consider bulk material, which is having conduction band and valence band. Conduction band is unoccupied state and valence band is of course occupied state. These two bands are closely lying bands. They are just overlapped on each other, like conduction and valence band in bulk material. So unbound electrons have motion that is not confined. But in scale, if we could decrease the size of this particular bulk material, there will be the conduction band and valence band have some different space in between the conduction band and valence band. That is nothing but the band gap, the separation between the valence band and the conduction band. So electrons motion becomes confined, and that's in the nanoscale material. That is the difference between bulk material and nanoscale materials. So material properties, we can say how bulk material properties are different from the nano with the same kind of material. Suppose we consider a bulk gold. If we could consider a gold material which is in the bulk form, it looks yellow. We can see the shiny surface of this bulk gold. But if we could change the dimensions, if we could go lower dimensions like 300 to 50 nanometer, the change in the color will be like the of this particular material can be changed from this golden to this blue. And if we could further reduce the size of this bulk material like 3 to 30 nanometers, it will be metallic. The form will be same as metallic, and the color will change. It will be red. And if we could go less than 1 nanometer, it will be non-metallic. Means as we change the dimensions of the bulk material, its properties will also get changed. Means as I mentioned in this gold example, means as we are decreasing the size, the number of the color of the that particular material is also getting changed, and the properties like up to 30 nanometer to 30 nanometer is metallic, but as we decrease less than 1 nanometer, it is becoming non-metallic at 1 angstrom. So here we can see the different sizes of gold nanoparticles like 30 to 90 nanometers, and at each size of that particular materials, the color has been changed. Means as the color is changed, the properties of that particular materials are also changed or varied. So bulk, here we can see the bulk gold is shiny or yellow metal, and nanoparticles appear to be red. So bulk gold does not exhibit catalytic properties. But if then we could go towards the preparation of nanoparticle of this bulk gold, it will be excellent low temperature catalyst. Means if we are going towards the lower dimensions of this material, we will enhance its properties, its catalytic properties of that particular material. So if we could take an example how these properties can be increased at the nano dimensions, suppose in case of physical properties, or if we could consider one physical point that is like physical properties to talk about. So here we can see the particle radius, how the particle radius is going to increase, and the metallic melting point is also going to increase. Means when we are at the tiny particle is equal to lower melting point. Means when the particle size is about 1 or greater than 1, between 1 to 2 nanometer, the melting point is also about 500 degrees Celsius. But as the size of this particle is radius is increased, also the melting point is also getting increased. So lower the temperature, lower the material, lower the melting point will be required. This is in case of the physical properties. In case of the chemical properties, if you could see, if we have a tablet and we just want to dissolve this tablet in a solution, it will take like 10 to 15 minutes. But you just crush this powder in the powder form and just dissolve it. It will just quickly get dissolved in just few minutes. So this is the difference between the bulk material properties, how the properties, chemical property, physical properties get changed of that particular material in the bulk form, and in the if we reduce the dimensions of that particular material. So in case of a mechanical property, like this is the bulk material and these are the nano material. So smaller the cross section of nanowire, the less is probability to finding or its imperfections. Such as here we in bulk material we can easily find the dislocations and it can change its properties. But in case of the nanomaterial, it is very difficult, or it is very probably there will be less imperfection or dislocations in the or impurities in that particular materials. So imperfection crystals are highly energetic and can eliminate small size, make such eliminations for imperfection possible. With these kinds of imperfections in the bulk materials, we can reduce or we can get tackle of these kind of bulk imperfections with the nanomaterials. So now history of nanomaterials, if I want to, if we could flash light on the history, because nowadays we are just hearing this nanotechnology word, but it's not a recent phenomena. It has a history. It is a very long back ago people were working on these things. We might have seen these kind of windows in the very old churches or old castles. This is the effect, or this is the phenomena, or this the magic of this multicolored is just because of the nanomaterials or the properties of that nanomaterials which are implemented in this kind of phenomena. How this works? Suppose we have there, as we could talk about the nanomaterial, when you have particular kind of nanomaterial, the transmitted light, the same nanomaterial will, when transmit the light, then the color will be different, and when these particular nanomaterials absorb, reflect the light, the color will change. Means depend on the property where the light is transmitted or reflected, same material will show the different colors, and accordingly we can see the different colors or different number of beautiful colors, different beautiful colors in this window. So 1,000 years ago, Chinese used gold nanoparticles as an inorganic dye to introduce red color into the ceramic. This is not a recent phenomenon. Means like from long ago people are using, but the introduction of that nanomaterial or the invention of this nanomaterial, the field has been just changed in this year. Before the field was different and now the field is different. So where we are getting in contact with the this technology related thing, that's why we are getting introduced with this nanotechnology. If we could say about the microscope, here you can see the animation, how the cup change, the color of that particular cup is changed. This cup is nothing but the microscope. It is a 4th century Roman glass cage cup made of the dichroic glass. So when it is showing red color, then if we could flash the light behind this cup, the red light is get seen. And when we light from the front, if we could flash light from front side of this cup, it will show the green color. Green means from the absorption, means the reflection and absorption, we can see the different colors of that particular kind of material. Or that particular dichroic gas is showing different properties when the light is absorbed and when light is reflected. Means red and the green. So red is transmitted light and green is in the scattered light. And this magic is happened due to just because of the nanomaterials. And the dichroic effect is achieved by making the glass with tiny proportions of the nanoparticles of gold and silver. Means here are tiny nanoparticles are included, like gold and silver, dispersed in collider from throughout the glass materials. That's why this glass is showing, this dichroic made glass is showing different colors at different absorption and transmission and absorption of the lights. This is the magic of the nanomaterials or low dimensional materials. So Michael Faraday has first made or say this, we can see here this nanomaterial, nano-colloidal solutions of gold at Royal Institution. In 1857, Faraday prepared gold colloids that was stable for almost century before being destroyed during the Second World War. These nanomaterials, here we can see the nanomaterials are also having the high quality of stability. They are stable for the, like it has told like about century it were stable. Means it has a great stability, it has a great chemical property, great physical properties and great electrical properties also. So naturally occurring, we have nanoparticles in our surrounding. What are these naturally occurring nanoparticles? Can be volcanic ash, it can be ocean spray, and fine sand and dust. In these also we can find the nanoparticles or biological matter like viruses, and man-made nanoparticles are like cooking smoke. In cooking smoke also we can find the nanoparticles, diesel exhaust. And welding fumes. From these are the man-made nanoparticles. In these kind of reactions also nanoparticles get formed. Or the industrial influence, if we could say the waste of industrial, there will be the formation of nanoparticles. So how to make? There are different kind of nanomaterial. There are number of examples of the nanomaterial like nanotubes, yolk shell, nanofibers, nanosheets, mesosphere structures, nanoporous fiber, core shell structures, metal organic frameworks, nanosphere. These are the examples of nanomaterials. And how can we prepare these nanomaterials? That is the issue. So there are two type of approaches to prepare the nanomaterials. One is the top-down approach, other one is the bottom-up approach. These two major approaches are carried forward to prepare these kind of number of examples of the nanomaterials. So we'll see what is the top-down approach and what is the bottom-up approach. So if we could talk about the top-down approach. Top-down means, here we can see in this figure only, top-down means we are going from top to bottom, and in bottom-up, we are going from bottom to top. So in top-down approach, like building something by starting with the larger component and cramming away a material. Means we are having a large material, and from that large material, we are making the smaller thing. That is the top-down approach. Means having big thing, and out of that big thing, we are making the smaller thing, that is like sculpture from a rock. So this is the top-down approach. This is just an example of top-down and bottom-up approaches. So in technology, if we could talk in case of nanotechnology, what is the top-down approach? Patterning or using photolithography, as Pasha sir explained about the photolithography. So that patterning and etching away material as a building integrated circuits. That is the top-down approach in the nanotechnology. The next is bottom-up approach. In bottom-up approach, what is happening? Building something by assembling small components. Means here we are having the small components and building all the small components together, we are achieving a big thing. Means suppose we are having making a building with the small bricks, and this is a small, just one, this is bottom approach, this is the bottom thing, and we are making big thing about this is the bottom up approach. Means we are going from to higher scale. This is the bottom up approach. And in nanotechnology, the self-assembly of atoms and molecules in a chemical and biological system. Means where a number of atoms and molecules come together and they form a chemical or biological system. That is the bottom-up approach in case of the nanotechnology. So the nanoscience and nanotechnology. Nanoscience is the study of nanomaterials, their properties and related phenomena. This is nothing but the nanoscience. Means here we are studying about the particular properties of these nanomaterials. How can we grow these nanomaterials and how their properties we can cultivate or we can modify these properties according to our requirements. That is the nanoscience. And nanotechnology is application of these nanomaterials in the devices and products to make the things possible or to get towards the application part. That is the nanotechnology. So incorporation of nanoscience into technology is nothing but the nanotechnology. So if we could think about or talk about the examples of how the nanotechnology has changed our world, even in the recent era, it has drastically changed the appearance of the materials. In our day-to-day life, we are using nanotechnology. How? Because if we could see, this is a transistor which was made and if we could say nowadays, the size of this transistor is like, suppose this is 1 centimeter square area, and there are number of thousands of transistors. Means this big transistor just get converted, like as Dr. Pasha has explained, as a photolithography. So with the help of this photolithography, we can make this transistor in just 1 centimeter square, thousands of transistor we can make. Means as the size of this transistor is getting decreased, of course the gadgets we are about to make or the whatever technological things, which will also get the reduce the size. The example of this nanotechnology, suppose we were having the library number of books, but nowadays we don't need a library. Like just you have to take one device, or where you can put all these books, you can just put in just one device. Why? Because the nanotechnology is helping to reduce the size of that particular things or particular devices. This was like we could have just a Kindle, and we can store number of thousands of books in just one Kindle, which is easy to carry, which is easy to read. Instead of this is how the world has been changed. If we could talk about the before we were having telephones, but nowadays we are having just a handy mobiles. With this size to this size is just the magical phenomenon of the nanotechnology. Nanorobots. If we could talk, just another example is about the cameras. Before we were having the big cameras, but nowadays everyone is having their hand camera wherever they go. You can just click the picture with the mobile. So this is how nanotechnology has changed our world. It has been entered in our life, and day to day, every day we are using this nanotechnological things, or this we are exploring this nanotechnology by our day-to-day needs. We are fulfilling our needs with the help of this nanotechnology. So it is not very different thing. This is the thing which we are using every day, but we are not just aware of what we are using. So this is what. So in summary about the nanotechnology, we can say nanomaterials are 1 to 100 nanometers. Nanomaterial dimensions are 1-dimensional, 2-dimensional, 3-dimensional. So nanomaterials are small and they are having better properties than the bulk material. That's why small is always good. And material properties vary with the size of material. Surface to a volume area ratio also get increased. Top-down and bottom-up approaches are the two approaches to prepare the nanomaterial. And we also see then how nanotechnology has entered in the electronics and how it changed the electronics world. So now how can we think green? Means suppose if we want to utilize this nanotechnology to prevent our world, thinking green. What is mean by think green? Green thinking means following the practices that can lead to actions and lifestyles to be more environmental friendly, and which can help us to reverse or preserve our environmental surroundings and our natural surroundings for future and the current generation. Means we can implement this nanotechnology to save our world and to get the more and more benefit for the world, and to just keep our environment clean for our current generation and our future generations with the help of this nanotechnology. So that is nothing but the think green. Means where we have to not explosive things. Means where we can also take care of the environment, and also we are going to go forward towards the technology. So as we know, these are the conventional, like these are the sources which we are using from long time, like kerosene, natural gas, propane, coal. These are the sources which are fulfilling our daily needs. So if we could go through these statistics, here we can see the yellow part is showing the natural gas, fossil fuels, coal. Means these are all are the natural resources which are highly using compared to the renewable sources or hydropower sources. Means these things are not renewable. These will get, as we are using, not stop our consumption of this material, they will get at the end. So as the population is increasing, the need or demand of these materials is also getting increased. These are not good. As population is increasing, these materials are not going to increase proportionally to the population. These will be get decreased. As population will increase, this material will get decreased. So we are just having a big burden on these material or these kind of sources for our day-to-day energy survival. So means if you could see by 2040, the world population will be increased from 7 billion to 9 billion. And the number of population increasing, the families will be double in the size. And as peoples are increasing, of course, the total energy demand will also get increased. Means the world is over there. The size of the earth is that much. Whatever power sources we are having, natural sources, they are the same. But the rate at which the global world population is increasing, these natural resources are having some limitations for their use. They are going to end. So what we have to think about something which some sources which can have the same advantages as natural sources, but don't have any kind of bad or adverse effect on the earth. So hydrogen is considered as a green energy source nowadays to fuel our cars, to heat our houses, to for different kind of vehicles as a fossil as a fuels to run our industries. Hydrogen is no green hydrogen is considered as a green source of the energy instead of other fossil fuels. And so how can we go for this approach? So if we could consider about the green hydrogen synthesis or a hydrogen synthesis to fulfill our energy needs, there are a number of different kind of hydrogen like brown hydrogen, gray hydrogen, blue hydrogen, and green hydrogen. So brown hydrogen is what? Which is product of the industrial processes. Gray hydrogen is the produced using fossil fuels. So these brown hydrogen and gray hydrogen are having the high carbon content. And if we could think the next part is the blue hydrogen. This blue hydrogen produced using fossil fuels, but CO2 is captured. So there is also lower carbon. But in green hydrogen, but green thinking, where we are using about the green sources, green energy sources. So green hydrogen is one of them. So green hydrogen is what? Where hydrogen is produced using electrolysis powered by renewable electricity or nuclear power. So and this kind of green hydrogen are also having the zero carbon. Means that is the sustainable option for the energy fulfillment of the energy need of the world. So this green hydrogen is also having the same applications as the fossil fuels or the whatever natural sources we are. They have the same efficiency, same power, same ability to work. Like with this green hydrogen, we can also fuel our cars. So it can be help in the energy storage, and also it can be used as an alternative fuel for the different applications. So other thing is like how can we produce this green hydrogen? There is one approach that is called the water splitting. We know the water we are using day to day. That is the most common thing in our day to day life, water, and it is available in the plenty abundant form. It is available. It's not like fossil fuels. Like fossil fuels are limited, or natural sources are limited on that, but water is in the abundant form. So we can just simply split. We know water is made up of 2 hydrogen and 1 oxygen molecule, like H2O. So if we could split this water into 2 different molecules, oxygen and hydrogen, so what will happen after separating this H2 and O2? This H2 can be used as a fuel, and this O2 can be just put in the environment, or it is a green source, or it would not have any harm on the environment. Means just by splitting, we can produce the green hydrogen with the water splitting. This water splitting phenomena is most widely used phenomena for the production of green hydrogen. So as we know, water is in abundant form. Means here we are not going to harass or do any burden on earth. We are just using the plenty of source which we are having. 70% of the earth is of the ocean, and it is a fantastical as the companies. Here we can easily use this source to produce the green hydrogen. So there are number of methods to use to produce the green hydrogen, like electrolysis, photocatalytic water splitting, and photoelectrochemical water splitting. These are the 3 approaches for the formation of green hydrogen. So in electrolysis, in electrolysis we can see there are 2 kinds. There will be like a cathode and anode will be used as electrolyzers to split the water. And in photocatalytic water splitting, means here we are using the electricity to split the water. In photocatalytic water splitting, here we are using the sunlight. The sunlight is also abundant source on the earth, so it can be easily available. So this means with all these approaches, we are not harming the earth. We are not making any bad effect on the earth. With this, whatever sources we are having, green sources, we are using these sources to make the green fuels. So photocatalytic water splitting, we will use sunlight to split the water and produce the hydrogen. In photoelectrochemical water splitting, this is a combination of electrolysis and photocatalytic water. Means where we are using the electricity also and the sunlight also to split the water and to make the green hydrogen. So first we will see about the electrolysis. What is meant by electrolysis? Here we can see the cathode and anode with the power supply. So what will happen during the electrolysis water splitting? The protons will adsorb on the surface of the cathode. This is a cathode. Here will be these protons will be get adsorbed, and the electrons are transferred from the electrode to the astral protons to from the hydrogen atoms. Means whatever electrons will be over there, these electrons will be get transferred to the electrode to adsorb the protons to form the hydrogen atoms. And when these two hydrogen atoms combine, they will form the hydrogen gas. This is the phenomena behind the electrolysis or electrochemical water splitting. And in the photocatalytic water splitting, here we can see the first we know photocatalyst. What is mean by photocatalyst? Photocatalyst is nothing but the material which will absorb the photon from the light and which will have energy equal or greater than its band gap. So it will excite its electrons from valence band to conduction band. And this excitation produce positive charge. Here we can see this excitation from electron from this valence band to conduction band, when it turns up, there will be the formation of the positive charge, or we can see as a hole and the valence in the valence band, and the of negative charge due to the electron into the conduction band. So what will happen? The photo-generated charges are then transferred to surface of the photocatalyst. Suppose this is surface, whatever photo-generated charges, electrons will be get transferred toward the surface of that particular material of photocatalyst, and which will be get absorbed into the water. And the holes in these holes will be get used to oxidize the water to produce oxygen, and electrons are used to reduce the water, which will produce the hydrogen molecules. In this way, we can split the water with the photocatalytic effect, and hydrogen is then captured as a gas and can be used as a beneficial purpose. So this is the phenomenon between the photocatalytic water splitting. And the next is the photoelectrochemical water splitting. As I said, photoelectrochemicals is nothing but the combination of electricity and solar light. So in photoelectrochemical water splitting, hydrogen is produced from water using sunlight and specialized semiconductors, or we can call it as a catalyst materials or photoelectrochemical materials, which will use light energy to directly dissociate water molecules into the hydrogen and oxygen. Means here we are using the photons also and the electrons also, electrical energy also, to split the water and to produce the hydrogen. So as I said here, photocatalyst material I said, or catalyst, all these things will be happening with the material which we are using, the particular material. Suppose we could call it as a catalyst. So catalyst is nothing but a substance that increases the rate of chemical reaction without itself undergoing any permanent chemical change. Means this catalyst will act as a energy giving material. It will not disturb the reaction. It will provide energy to that particular reaction, but it will not undergo any permanent change in that permanent chemical change in that reaction. It will only boost the rate of reaction. Okay. So this is nothing but the catalyst. So catalyst increases the rates of reaction by lowering the activation energy. Means here we will need the low energy, but the rate of the reaction will be get increased. This is how we can see here is a activation energy with catalyst no present, but when the catalyst activation energy with no catalyst present and with the catalyst present, means how this catalyst can help to, means here energy consumption is less, but the results or whatever output we are going to have, they will be high. This is about the catalyst. So the goal of the catalyst means what kind of catalyst we have to choose to fulfill all the necessary requirements of that particular application. So the catalyst means the development of cheap, highly active and stable catalysts that provide your 100% selective towards that particular reaction to get a target product with limited production of chemical waste and with minimal use of energy. Means ideal catalyst what? Is the material which we want to choose. Before choosing the material, we have to take in account the things like the material should be cheap, it should be highly active, it should be stable, it should give a 100% selectivity, and it should not produce any chemical waste, or it also use the minimum energy. These are the properties of the ideal catalyst. So there are two types of catalysts: inorganic catalyst and organic catalyst. In inorganic catalyst, there are gases, metal oxides, inorganic acids and bases. And organic catalysts are like organic acids or enzymes. So if I could talk about the inorganic catalyst, here we can see the different volcanoplasts. If I could go through the first volcanoplant, here we can see number of different metals and according to their activity. Suppose here at the top, we can see the platinum, palladium, silver. These are the materials means which are having the high activity. Like we can also call them as a noble metals. So platinum, palladium, gold, silver, these are the materials which are having the high activity, and also they don't disturb any kind of reaction. They will just increase the rate of the reaction without involving themselves into the reaction. So nowadays, like metal, if we could talk about inorganic catalyst, we can say metal are the ideal materials. Noble metals are the ideal materials to involve or use as a catalyst for the different kind of reactions, like metal oxides, metals. So how can we go for this material? Like if we could say, we already discussed about the nanotechnology, the bulk materials, how these nanomaterials will achieve different properties. If we could say this is a particle which is about greater than 8 nanoparticles. So suppose we could consider as a bulk material. If we could reduce its size 2 to 8 nanometer, it will be nanoparticle. If we reduce the nanoparticles further 2 to 30 atoms, here I'm talking about the atom. Nanoscale is up to this. But beyond that, when we these are called the nanocluster, means where we are having 2 to 30 atoms bulk together. That is the nanocluster. And further, if we could reduce, go towards the further dimension, it will be ADSMC, means atomically dispersed single metal catalyst. Here we can having the few atoms, and if we could reduce this size, further reduce the size of this material, it will be single site heterogeneous catalyst. And if we could reduce the size of this material further, it will be single atom catalyst. Means we can see only single atom, only single gold, or so only single atom of silver we can use to carry out the reactions, or to use it as a catalyst for the different kind of reactions. Means as we are decreasing the size, we can get the more and more benefit of that particular material. We will also reduce the cost of the material, and also the materials, whatever material we will be using, it will be in the less quantity. So if we could talk about the single atom catalyst, so compared to this bulk material, single atoms can be recyclable. They will have low cost, high homogeneity, high durability. Here we can also the high atom utilization efficiency, means each and every atom we can utilize with for the particular reaction with this kind of approach. So the single atom catalyst, which is less than the nanoscale. So these nowadays single atom catalysts are also playing very important role in different kind of reactions. Like they are working as heterogeneous catalysts for hydrogen production, oxygen production, hydrogen peroxide production, nitrogen reduction reaction, carbon dioxide reduction reaction. With these kind of reactions, we can achieve a green energy goal, where we are not harming the earth, we are not harming our environment, and we are utilizing the things which can be better, which have the better impact on the environment. So if we could talk about the single atom synthesis, or there are few approaches for the synthesis of single atoms, but here I just took as one example where the nickel ions or nickel single atoms or nickel cobalt single. Now here we were talking about the single atoms, but if we could take the two different single atoms, suppose one is gold, another one is silver, where when we have two different single atoms, two different material single atoms, it can be called as the dual single atoms or single atom dimers. With means where different combination, we are using different combination of different metals, we can use, or we can explore all the properties of that particular materials, and we can enhance the reaction rate. Means if we could see this dual atom synthesis, after synthesis, this is same as I explained. This is the electron microscope, high definition scanning transmission electron microscope. With this kind of only this kind of microscope, we can see the atoms. Here we can see the yellow mark. These bright dots are nothing but the atoms. So we are utilizing the atoms, means from bulk to directly towards the atom we are traveling, and we are utilizing atoms for the as a catalyst for the water splitting. In our application, we can say as a water splitting. So single atoms, here we can see like how the single atoms or low dimensional material are different from the bulk material. This is nothing but the hydrogen evolution reaction graph. Here we can see which can be drawn by the potential versus the current density. Means at what potential you are producing that particular hydrogen. So here we can see nickel cobalt, the catalyst which we seen in previous, it is showing better production or better potential compared to the other bulk materials or other materials, because due to its the less size and the combination of two different atoms together. And here we can see the potential means at what potential, that potential, there are certain parameters which we have to consider during the water splitting. If we are going for the electrochemical water splitting, we have to think about the potential, at what potential the potential should be very less, because we don't want to consume high electricity, we want to go for the green approach. So there will be the consumption of the energy should be very low, and we could have the good less over potential. With that less over potential, we can get the maximum benefits. So if we could see there over potential versus the materials, as how the means this nickel cobalt single atom dimer is showing better compared to the better or less over potential compared to the other materials. With this graph we can observe that the nickel cobalt single atom dimers, where we are using single atoms, compared this is about the nanoparticle. That means we are going beyond the nanoparticle, that is single atom. If we could consider this approach or compare the approach of these two materials, single atom dimers are showing low over potential compared to the nanoparticles. Means these are having the good potential to split the water, and also a green way to or a better way, better energy, better power to synthesis the green hydrogen. This is for the hydrogen evolution. Means here hydrogen is getting produced, and this is about the oxygen evolution reaction. In means where oxygen is getting produced. Here also nickel cobalt single atom dimer is showing the better results compared to the others, and the over potential is also less over potential values compared to the nanomaterials and the with this single atom dimers. So this is how we can see the eye-opening difference between the single atoms and the nanoparticles, or compared to the bulk materials, we have more higher over potential compared to the nanoparticles. This is how, as we are going towards the lower dimensions, the dimension has changed, the materials properties are also getting changed, and we are getting more and more benefits with that material. So like I was working on the synthesis of copper palladium bimetallic single atom catalyst, where I used copper and palladium, two different single atoms, and they are modified on the glassy carbon electrode with the nitrogen doped graphene. Nitrogen doped graphene is used as a substrate, as a base material to deposit this CuPd single atom catalyst, bimetallic single atom catalyst for the electrolysis. So this will be my cathode, where actual hydrogen production will be done, where I'm having the nitrogen doped graphene with the decorated with the copper and palladium single atoms to form the hydrogen. So I also undergone two approaches for the synthesis of this material bimetallic single atom. So one is these two synthesis the material to synthesis the catalyst. There are two approaches. One is chemical approach, another one is electrochemical approach. In electrochemical approach, you are using the electricity, you are giving some power, you are applying some potential, measuring some current. This is related to electrochemical. And in chemical approaches, you are using some chemicals, more chemicals, some temperature, some different kind of parameters also, like physical parameters like stirring, heating, these kind of parameters also applied for the synthesis of material. So electrochemical method is always a green technique for the synthesis of material compared to the chemical approach, because in chemical approach there will be the formation of some byproducts which are kind of harmful to the environment also. So electrochemical approach is always considered as a green approach. In the electrochemical approach, you will have 3 electrode system where working, reference, and counter electrodes will be used. And on working electrode, you deposit, or you could create synthesis your material. So this is the electrochemical approach. And in chemical approach, you have to different. Here also we are using the materials like precursors, we can say copper and palladium, and we are making it so just solution of this copper and palladium in some acidic media, and we are using it as an electrolyte, and just using 3 electrode system and applying some potential, particular constant potential, to get deposited material on our working electrode. And this is how it looks. But in chemical approach, we have to do some different kind of we have to add some other approaches also, like stirring of the material, then heating of the material at particular temperature with some particular environment like nitrogen environment, argon environment, to felicitate that material to get that particular properties. So this is how we can use the chemical approach and the electrochemical approach for the synthesis of material. And I used both the approaches for the synthesis of my particular kind of material, CuPd bimetallic single atom catalyst. And here I used it for the hydrogen evolution reaction. If I could see the onset potential means what? The potential at which the hydrogen or oxygen is getting produced, has started to produce. So if I could consider is about minus 0.2. So both the materials are showing the same results. There is a kind of difference, but it is very minute difference. So of course, if chemical and electrochemical both are showing the same results, I will always go for the electrochemical as a green synthesis technique. So I also utilize the same material, copper palladium, for the hydrogen evolution reaction and oxygen evolution reaction. And here I compared it the bimetallic with the single atoms also, is where I use two metals, copper palladium. I compared it with the only copper, only palladium, and as I seen, the copper palladium combination of two single atoms is showing better results compared to the other metals. And it is also having the low over potential. Same in the case of the oxygen evolution reaction. Means here it is for the hydrogen production, this is for the oxygen evolution reaction. And means when we are combining two different or single atoms together, we are having the better properties, or we are getting the better results compared to the other single materials. So
Hello.
if we could state, means like nowadays people are working tremendously or explore. Yes, sir.
Are you able to? Am I audible, madam?
Yes, sir. Yes, sir.
Continue with your lecture.
Okay, sir. So if we go to the current state of the material, this kind of material study means like researchers are exploring these kind of single atom. Means nanotechnology is like a different era compared to the single atom, because nanotechnology, we are about nanomaterials, but single atoms is beyond the nanotechnology. Means we are whatever advantages we were having in nanomaterials, we are having the better than the nanomaterials in the single atom. That's why the researchers are engaging their efforts to utilize the single atom materials for the green energy synthesis, or to synthesize different kind of green fuels to fulfill the need of our society or the global need. So this is how there are different reports. We can see the recent reports from the like reputed journal like Nature Communication and Givante. People are using these kind of single atom catalysts for the different hydrogen evolution reaction, oxygen evolution, to produce the hydrogen, and having the advantages over the nanomaterials and the bulk materials. So this is how we can contribute towards the green future, or we can create the green future to the next generation with these kind of approaches of nanotechnology, how we can implement this nanotechnology to our day-to-day life. So this is what I wanted to say. Thank you. Hello, sir.
Thank you, madam.
Yeah, I'm done.
Thank you, madam, for your nice presentation.
Yes, sir.
Please turn on your video.
Okay.
Thank you very much, madam. It was a very nice presentation, and you are doing nice work in the field of nanotechnology.
Thank you, sir, for your nice words.
And we are thankful to you for accepting our invitation on behalf of our Shivaji College, and coming over online in this conference and delivering a nice talk. Thank you very much.
Thank you, sir, for having me. Thank you, sir.
Questions which are occurring.
Participants, so you have any questions, you can ask.
Hello.
Yes, sir.
Ask
Hello,
your question.
Ma'am, I have a doubt. I have a small doubt, ma'am.
Yes, sir.
Ma'am, I have read in many places, and you already mentioned that the size of nanoparticle.
Dear participant, ask your question or post it in the chat box.
Ma'am, am I audible?
If you are not able to
ma'am, you
ask your question, post it in the
mentioned that the size of a nanoparticle ranges from 1 to 100 nanometer.
Yes.
But I have seen in many cases that the diameter of, if the diameter of a rod is around 200 or 250 nanometer, it is still called a nanorod.
It depends, means ideally nanoparticles means what where we are having the very low dimensions, as I told, in 1 to 100. Now it depends on the properties of that particular material. So as you are told, like 200 nanometers, yes, if it is in the 200 nanometer, also we can call it as a nanomaterial. But ideally we have to consider in between the 1 to 100 nanometers. Suppose we want to go for the if we could take an example of the single atom, when we can call a single atom, when it will be in the angstrom scale, when it will be less than the 1 nanometer, then we can call it as a nanomaterial. So same, if it will be less than the micro scale, it will be nanomaterial. So I just ideally put 1 to 100 nanometer can be called as a nanomaterial.
Ma'am, if possible, can you share your presentation?
Sorry.
If possible, can you share your presentation in our group, WhatsApp group?
Okay, I will say. I will let
Thank
you.
you. Thank you.
Thank you.
Madam, there is a question in the chat box. Which software have you used for data interpretation?
I generally use Origin for the data plotting, and further interpretation we can just do from the graph which we were having from the plot of that graph. I just use Origin for the plot and the interpretation.
Okay. Mr. Pratik Sawant, do you have any question? Mr. Pratik Sawant, can you hear me? I think we are not able to connect with Pratik Sawant. Okay, sir.
Yes, sir. Yeah. Yes, sir.
Is it Pratik Sawant?
Hello.
Sir, make it fast. Ask your question.
Yes, sir. Ma'am, I had a question. I'm working on photocatalysis. Can you hear me, ma'am?
Yes, I can. Yes, you are audible to me. You are not audible to me. Hello?
Hello.
Make it fast, Pratik Sawant. We are running out of time. Ask your question.
So, madam, I'm working on photocatalysis field. I'm this thing synthesizing TiO2 right now. So, what do you suggest to really focus on? Like many properties affect the photocatalysis, right? The particle size, the porosity, and band gaps, and all these things. What is the single most major thing that affects the photocatalytic activity, would you say?
If we could talk about the TiO2, as you are said, like TiO2 is an ideal material for as a photocatalyst. It acts as an ideal photocatalyst because due to its electrical energy, to its band gap. So if you want to increase the properties or increase the application part of this material, you can dope these materials with some other kind of materials, with some other oxides, or you can just tune this material to tune the band gap of this material. Means you can further reduce band gap of this material for the better photocatalytic activity by just doping with the material, or by just combining the material with other, or maybe the also we can tune the band gap of this material with the different dimensions. Means if we are going for the different nano architecture, means like nano materials, nano quantum nano wires, nano shells, or core shell like structure. Means with this kind of approach also we can tune the band gap of this material, and by the tuning of band gap we can of course have better photocatalytic properties of that material we can achieve. Means one is doping, and also another one is the what kind of nano form you are using of that particular material. It will affect your properties of the material.
Yes, ma'am. That was my question. Exactly, like if you change the surface morphology, like you change the pore size and you change the porosity of the material, you have more sites for reaction, right?
Yes.
That is one aspect of it. And second aspect of it is the band gap. When you tune it to the visible region, you get the absorption in under visible light. So when you build a efficient photocatalysis of catalyst, what is more important, building it in a visible region or building it more efficient in the UV region? What is
of course it will be more beneficial according to me, like to build it into the visible region, to get the whole spectrum of light, and to easily whatever easily available. This way we can consume the whole light spectra and we can get the output, better output. Actually,
Okay,
people.
okay, madam. Thank
Actually,
you.
yeah.
I request now Dr. Yemakar sir to propose vote of thanks.
Thank you, Kalamse sir. As we conclude the third session, Dr. Megha Deshmukh ma'am, interesting presentation on nanotechnology, the future of green energy. It's my privilege to extend a sincere vote of thanks to all who have contributed to the success of this enlightening session. First and foremost, I would like to express our heartfelt gratitude to Megha Deshmukh ma'am for her insightful and inspiring presentation. Your expertise and passion for the subject have shed light on the immense potential of nanotechnology in concrete the way towards a sustainable and greener future. Last but certainly not least, I want to thank all the attendees for their presence and active participation in this session. Once again, thank you one and all.
Thank you.
Thank you, madam.
Thank you.
So now we are in the last segment of this e-conference, that is validity function. We have Dr. Kamalakar Khanse sir, Chairman Board of Studies in Physics and Principal Lal Bahadur Shastri College, Ahmedabad. For this validity function, as the President, we have the Vice Principal of our college, Dr. Nitonde sir, who is also Chairman Board of Studies in English. First, I request some of the participants who have attended this conference to express their views. If you have to make some comment on the conference which we have held, you can express your views. Someone from the participant side, I request to express their views about the conference. Is there anyone who would like to express?
Any participant who is willing to express his views on the today's international conference? Hemant, connect him.
I am audible, sir.
Yes. Please go ahead, Hemant.
I am Mr. Hemant Suryavanshi. I am assistant professor in physics, Arts, Commerce, Science College, Thane. Today's conference is a very organized conference, and nowadays that topic is a very important topic for our changing, suddenly changing that.
You can turn on your camera, Hemant.
Okay, sir.
If possible.
Okay, sir. Yes.
This
topic of the conference is a very important nowadays, because we are changing nowadays. Field of research is changing. And that's why that conference is a very important for all of us, and organization of that conference is a very well. And I am seeing from the last 15 to 20 days, Dr. KCT sir and all their committee is taking our helping for our registration process and all that things. Thank you, sir, for organizing such a nice conference.
Thank you, Hemant. Is there anyone? Kailas?
Yes, sir.
Kailas Morale?
Yes, sir.
You want to say something?
Yes, sir.
You want to say
Sir,
something?
conference-
Go ahead.
Yes. Right from the registration to the end of the conference, everyone have supported for the conference, sir. And the topic which was selected was very nice. And thank you everyone, sir, for introducing all of us research students for very nice and interactive talks. Thank you, sir.
Thank you, parents. Thank you. Is there anyone? Is there anyone who want to express his views?
Is there anyone who want to express their view? Please come and.
Okay, we go ahead with the next part. I request the convener of this one-day e-conference on material science, recent trends in material science, Dr. S.N. Shetty sir, to present the report of this conference.
Good afternoon, one and all. I am Dr. S.N. Shetty, convener of this conference. I am here to present before you the report of today's conference. The conference began with the inaugural session. The conference was inaugurated at the auspicious hands of Dr. M.K. Patil, Senior Professor, In charge Dean, Swami Ramanand Tirth Marathwada University, Nanded. It was attended by the principal of the college, Dr. B.U. Zadav, head of our CDC, Hemant Rawji Zamkar Sahib. After the inaugural session, in the first invited talk, the talk was delivered by Dr. Pasha Sayyed from American University of America, Sharjah, United Arab Emirates. He delivered his talk on functional nanomaterials and advanced sensing device applications. Then the second invited session was conducted, and the invited talk was delivered by Dr. Gangadhar Banappanwar from Physics Department, Durham University, United Kingdom. The topic of his talk was Organic Optoelectronic Devices, Excitation, Transport in OLEDs. In the concluding section, in the previous session, the talk was delivered by Dr. Megha Deshmukh from VSP Technical University, Ostrava, Czech Republic. The topic of her talk was Nanotechnology, the Future of Green Energy. The seminar or this conference went ahead as per our plan. It was an overwhelming response from the participant side. More than 200 participants registered for this conference, and 60 research papers were presented. Were sent to us for publication, and they will be published in international scientific journal for science and technology in this week in a special issue. The number of papers itself indicate that a large community of scientists and engineers are working on this topic, that is material science and engineering. That is why we feel justified that this topic that we have chosen is a hot topic, and it was beneficial to one and all. There were 11 participants who joined from foreign countries, and about 195 participants from various parts of India who joined our conference. I express my gratitude to the management of our college, president of our institute, Honorable Prakash Dada Solanke Sahib, secretary of your institute, Satish Bhau Chavan Sahib, head of the local governing council, Honorable Hemant Rawji Zamkar Sahib, our principal, who is a source of inspiration for us. Without his support, we wouldn't have been able to deliver this conference in the manner we have delivered to you. Is none other than Dr. B.U. Zadav. I am also thankful to my colleague, Vice Principal, Dr. Rohidas Nitonde, my colleagues, co-convener, head of the Department of Electronics, who has written our college theme song, Dr. Ravi Shankar Jingre sir, Organizing Secretary Dr. Enorkar sir, Surendra Enorkar, organizing co-secretary Dr. Vijay Kalamse, who conducted all the proceedings, all the staff members of our college, the advisory committee members, non-teaching staff of our college, and I am thankful to all the participants for their overwhelming response and support for this conference to be made successful. I once again thank one and all for your support. Thank you very much. With these few words, I end up my report. Thank you. And over to Dr. Last but not the least, we had. Hello. Last but not the least, I forgot to take the name of our former student, Mr. Vijay Kiran Narwade, without whose support and help, it wouldn't have been possible. He himself talked with the resource persons and made it possible that these resource persons are available for this conference. I am thankful to Dr. Vijay Kiran Narwade and all the people who directly and indirectly supported and helped us to conduct this conference. Thank you very much.
Thank you, sir, for your brief report of this conference. Now we have with us our chief guest for this valedictory function. Dr. Kamlakar Kanse, sir, Principal, LBS College.
LBS College.
Sir, तुम्ही या इथे.
Okay. Now I request the chief guest for the valedictory function, Dr. Kamlakar Kanse, sir, to put his remark on this one-day e-conference on material science. Kamlakar Kanse, sir. Kanse, sir, please turn on your mic, sir.
Thank you, Dr. Kalamse, sir. I am audible. Hello.
Yes, sir.
Vijay, I am audible.
Continue.
Yes, yes. Okay, okay. Thank you, sir. Thank you, sir. Good evening, one and all present over
You
here.
are audible, sir. You are audible, sir. Continue.
Okay, right, sir. Thank you. Good evening, one and all present over here. It is a great pleasure for me to be here as a guest for the valedictory function of this one-day international e-conference on recent trend in material science, organized by the Department of Physics and Electronics of one of the famous colleges of our region, Sri Shivaji College, Parbhani. Principal B.U. Jadhav, sir, convener of this conference, our BOS member, Vice Principal, Professor S.N. Keseti, sir, with our Dr. R.P. Jingre, sir, who is wrote very great song, Manus Ghadto Yethe. R.P. Jingre, sir, Professor S.M. Enorkar, sir, with this Vijay Kalamse, sir, our Chairman of English, Dr. Nitunde, sir, all the professors, delegates, and research students from the various part of the Maharashtra and India. पुन्हा एकदा मराठी भाषा दिनाच्या निमित्ताने आज प्रथमतः सर्वांना मी मनपूर्वक या ठिकाणी सर्वांना राम राम करतो. सर्वांचं या ठिकाणी मनपूर्वक अभिनंदन करतो. First of all, I would like to congratulate Principal B.U. Jadhav, sir, convener of this conference, Professor S.N. Keseti, sir. Last 10 years, they are also one of the BOS member, active BOS member of the physics, with this one, Professor Patil sir, BOS member, along with this one, Girish sir, Yadav sir, Santosh Yadav sir, all BOS colleagues, organizing committee of this conference for the successful organizing of this international e-conference. This is a very good platform to share the research work from eminent scientists for new researchers. In a very short time, the conference is nicely organized on e-platform. In the first session of this online conference is inaugurated by our Dean of Science and Technology, Professor M.K. Patil sir. Professor S.N. Keshetty sir gives introductory speech. In his introductory speech, he explained the purpose of this conference. He discussed various materials, applications of these materials for the quality improvement in the life of human being. Professor M.K. Patil sir gives his inaugurator speech. He said the conference is organized on National Science Day. This day is celebrated as a birth anniversary of great Indian scientist Sir C.V. Raman. Then he discussed the experiment by the Raman, and almost we are familiar with the in atomic and molecular spectroscopy. What is the role of the actually we have to study the spectroscopy. In that one, what are the Stokes, anti-Stokes line? What is the Zeeman effect, normal Zeeman effect? So they have discussed on the very important topic, Professor Patil sir, and this material for the quality improvement in the life of human being. Professor M.K. Patil sir gives his discussion on the Raman effect. He also focus on current advanced research field like biotechnology, space technology, and pioneer in the research field, that is nanotechnology. Various materials, smart materials, application of materials, science in the optoelectronics in drug delivery tissues. After that, there was 3 technical talks was delivered by the resource person from UAE, UK, and Czech Republics. They focus on the nanomaterial for the sensing device application, optoelectronics device like OLED, and use of nanotechnology, green energy. I hope participant will take a lot of new ideas and knowledge from this conference. New education policy supports the blended mode of the education, that is offline and online mode. So organizing such conference, e-mode will be fruitful for to give the research idea and knowledge, advanced technique in the material, use of the nanotechnology for the upliftment of the society. Finally, I congratulate all organizing committee member of this conference for grand success of this conference. I am very much thankful to the organizers for inviting me a guest for this valedictory function. With these few words, I conclude my views about the conference. Thank you once again. Thank you.
Thank you very much, Dr. Kanse sir, for your kind words and expressing your views on today's conference. Thank you.
Sir. Thank you. Thank you.
Thank you, Dr. Kanse sir. Now at the end, I would like to request the statement for this function Vice Principal of the college, Dr. Nitonde sir, to express his views on this one-day conference.
Honorable Principal Dr. Am I audible, sir?
Yes, sir. Yes, sir.
Yeah.
Yes, go ahead, Nitonde sir.
The Honorable Chief Guest for the valedictory function of one-day international e-conference on material science organized by our Department of Physics and Electronics, Principal Dr. Kalamse sir, who happens to be the chairman board of studies in physics of Swami Ramanand Tirth Marathwada University, Nanded, the honorable principal of our college, Dr. Balasaheb Jadhav sir, the convener of the conference, and our mentor, Professor Dr. S.N. Keshetty, who is also vice principal of the college, the eminent resource persons who have joined in this conference since morning, as well as the delegates, participants, organizing team, and fellow friends. Indeed, it gives me a great pleasure to be a part of this conference and have a dialogue with you all. I know, being a man of letters and literature, there are some of my limitations to be amongst the physicists, those who are discussing material sciences from the morning. Friends, in this globalized world, wherein we have turned the whole world into a small family, it is a challenging situation for the wonderful teachers like you and me to provide universal opportunities and worldwide exposure to the world-class faculty, as well as recent trends in our topic to our students. And that is why I think teachers like Professor Keshetty sir, Professor Jingre sir, and their team, they have decided long back to go for such a venture. And today we could see that this venture has come into reality. We are at the concluding ceremony of this one-day conference on material science. Friends, such kind of activities, they give opportunity for our students and researchers to learn so many things from their peers. So it is not only the resource persons, those who guided the participant students, faculty members, and the research scholars. Among the peers, they can learn, and this kind of peer learning promotes them to take on advanced projects on the ideas that are tinkering in their minds. And so I believe that such kind of conferences, they are the seeds that would be resulting into the germination and later on some sort of innovations.
Sir, audio.
ऑडिओ येत नाही येत नाही का
ऑडिओ गेला
हो
ऑडिओ गेला
येऊन गेला
National economy, as well as the upliftment of science and technology. When the academic research comes to the applied level, when it is for the benefit of the society at large, when we turn out our research theories into the small applications that are needed by the members of the society, then our research creates an impact, and such type of impactful researchers were invited by Professor Keshetty sir in this today's conference. See, 3 resource persons from 3 diverse backgrounds, as well as the 3 aspects of material sciences. The first speaker who spoke from UAE, Pasha Sayed, dealt with the nano functions of nanomaterial. The second speaker, Gangadhar Bannapwar, who spoke about the OLEDs, and the last speaker, Megha Deshmukh ma'am, she spoke about green energy. I think the concerns of all the 3 speakers, though they were for the physicists, they were talking about technical terms, but for layman like me and many other stakeholders in the society, for them or the undergraduate students of the colleges, they would take away simple things that what we are in need these days is everybody is running after the renewable resources. Material has its own limitations. Material is not going to be unlimited. natural resources are limited, and how to overcome with this problem of limited natural resources with unlimited needs of human beings. So settling this matter, the researchers, the scholars, those who are working on material sciences, they are going to give the solutions. When your research is dealing with some problem and it provides solution to certain problems, then that kind of research is for the betterment of the society and community, and we are looking for such kind of research. I am sure that in today's e-conference, all the speakers, they have enlightened young minds, those who are aspiring to be the budding scientists, and they will also take certain steps forward, and they will be taking upright way in their future career regarding the material science and its research and applications. Once again, I would like to congratulate our organizing team for this wonderful organization. See, friends, it's not an easy task to bring out the 3 speakers from 3 time zones. Most of the times we have to calculate from GMT onwards, and not only the participants from the 3 time zones, but also participants from 10 to 11 countries of the world. So this has made the conference really an international one. Though we are meeting each other on virtual platform, but the advancement of technology, the ease of information communication technology, the ICT that we are handling, we never felt in the last 5 hours that we are far away from each other. Though we are miles and kilometers away from each other, but the ease of technology has made us feel that we are there in the single room, and with the Zoom room that we have discussed the things, and the technical idea that came from Professor Yenorkar sir to make it a live stream. I am sure that the live stream of this conference for the whole day, it would be there on YouTube channel of our Department of Physics and Electronics, and that would be helping many students or generations of our students, those who would require any reference to the quality content on material science. With these few words, once again, I thank the organizers for giving me an opportunity to be with you for this valedictory function. And on behalf of the administration of the college, I really appreciate the efforts taken by the organizing team, and I appreciate their efforts, and I congratulate them for such a wonderful conference. Thank you, and have a happy learning and wonderful research career ahead. Thank you.
Thank you, Dr. Nitonde sir. Thank you.
Thank you, Dr. Nitonde sir, for your encouraging words. Now, at the end, I request Dr. Yenorkar sir to propose the vote of thanks.
Thank you, Kadamse sir. Very good afternoon to you all. As we conclude this momentous online international conference, it is my honor to extend a heartfelt vote of thanks to all who have contributed to the success of this remarkable event. First and foremost, I would like to express our deepest gratitude to our principal, Dr. B.U. Jadhav sir, Dr. K.S. Kanse sir, Chairman BOS in Physics, Vice Principal, Dr. S.N. K. Shetty sir, Convener of this conference, Vice Principal R.S. Nitonde sir, for delivering the valedictory remark. Your insightful words have provided us with a profound perspective on the significance of this conference and its impact on our academic community. I extend my sincere appreciation to the organizing committee for their meticulous planning and tireless efforts in bringing this conference to realization. Your dedication and commitment to excellence have ensured the smooth execution of this event, despite the challenges posed by the virtual format. a special word of thanks goes to our esteemed speaker for sharing their expertise and knowledge, which has inspired and enlightened us throughout the conference. Your contribution have been invaluable in fostering meaningful discussion and advancing our collective understanding. I want to express my gratitude to all the participants who have joined us from around the country and abroad. Your active engagement, thoughtful question, and diverse perspective have enriched the dialogue and made this conference truly impactful. To the technical team, I extend my appreciation for your outstanding support in managing the online platform and ensuring a seamless experience for all attendees. Last but not least, I want to thank each and every one of you, our audience, for your participation, enthusiasm, and dedication throughout the conference. Your presence had made this event truly memorable, and we are grateful for the opportunity to learn and grow together. Once again, thank you to everyone who has contributed to the success of this conference. Thank you, one and all.
जाता जाता परत एकदा आपल्या सर्वांचे आभार मानतो. आज मराठी भाषा दिन आहे. आज मराठी भाषा दिनाच्या सर्वांना शुभेच्छा देतो. उद्या राष्ट्रीय विज्ञान दिन आहे. राष्ट्रीय विज्ञान दिनाच्या ऍडव्हान्स मध्ये सर्वांना शुभेच्छा. आणि काही सूचना आहेत तिथे. हे कॉन्फरन्स आता कन्क्लूड झाल्यानंतर फीडबॅकची लिंक टाकण्यात येईल ग्रुपवर, आणि ती उद्या दुपारी 12 वाजेपर्यंत आम्ही ती फीडबॅकची लिंक चालू ठेवू. आपण सर्वांनी फीडबॅक द्यावा आणि फीडबॅक अनालिसिस केल्यानंतर सर्वांचे फीडबॅक आल्यानंतर आम्ही सर्टिफिकेट्स देऊ. त्याला 2 ते 3 दिवस लागतील आणि त्यानंतर एक साधारणतः 8 दिवसाच्या आत आम्ही आपले पेपर पब्लिश झालेले ऑनलाईन व्हॉल्यूम या ग्रुपवर आपल्या इंटरनॅशनल कॉन्फरन्सच्या ग्रुपवर टाकण्यात येतील. तर सर्वांनी सहकार्य करावे. आपण आतापर्यंत सहकार्य करतच आलेले आहात. यापुढे आपल्याकडून सहकार्याची अपेक्षा करतो आणि तुमच्या सर्वांच्या सहकार्याविना हे एवढं मोठं कॉन्फरन्स घेणं शक्य नव्हतं आणि खूप मोठ्या प्रमाणावर तुम्ही आम्हाला प्रतिसाद दिलात, सहकार्य केलात, त्याबद्दल परत एकदा आपल्या सर्वांचे आभार मानतो. आणि जेव्हा केव्हा परभणीत येताल त्यावेळेस श्री शिवाजी महाविद्यालयाला अवश्य भेट द्यावे असं सर्वांना निमंत्रण देतो आणि मी आपली रजा घेतो. जय हिंद, जय महाराष्ट्र. आणि इथं मी मीटिंग एंड करतो.